Hi, it's time for another math easy solution. Today we're going to discuss further into infinite sequences and series. In my earlier videos, I went over extensively on this, and now I'm going to go over a review and true and false quiz, which is at the end of the chapter of my calculus book on this section, infinite sequences and series. I haven't done this before, this review and true and false quiz, but I think it's very good to get a recap, especially for me because I haven't been doing any math videos for quite a while, so just getting back into the groove. And also note that I have a Telegram channel now, so make sure to follow that MES Links Telegram channel. So t.me/MESLinks. Basically, I throw in there all the links, videos, images, etc. that as I see them that are interesting, and basically as I'm researching, I just throw everything in there for reference. And it's and if you want to see how my mind is day to day, you could go and check it out. Anyways, continue further. So like always, if you don't have time to watch this whole video, in this case, yeah, there's no summary and conclusions, but you could play this video at a faster speed, and there's some tips on how to do that. Because yes, your brain does get used to faster speed, which is pretty epic. And also you can download and read the notes, and also read the notes on the Hive blockchain. All the links will be in the description below, and you can also watch the video in parts, and all the timestamps of all the timestamps of all the parts and questions will be in the description, and so on. So let's just continue further. So note, as always, calculus book reference. Note that I mainly follow along the following calculus book. So Calculus Early Transcendental, 7th edition by James Stewart. Note the previous videos I used the 6th edition, and then some earlier, super early ones were actually earlier editions. Anyways, let's continue further. And yeah, now go over the chapter review and true and false quiz. So at the end of most chapters of my calculus book, there is a review section and a true and false quiz. Since it has been about a year since my last math video, I think it would be best to go over this review as a refresher on all things infinite sequences and series. So now let's take a look at these topics to cover. So yeah, basically the first section is review, concept check, and there's going to be 12 questions. And I put this, make this list right here because eventually I put these, make timestamps when I put them in the video description below, so you can go see the timestamps for every single question. So there's 12 questions on the review, concept check, and then there's a true and false quiz. There's a whole bunch of questions. There's 22 questions in total. Again, I list them all out like this so I can put the timestamps in the description. So let's take a look now at review, concept check. Alright, so the question one is, this is 4 parts of this question one. What is a convergent sequence? And then B, what is a convergent series? Notice the difference, sequence and series. Series number is a sum. This one is just a list of numbers. What does limit as n approaches infinity of an equals 3 mean? So this is the sequence right there. And then here, D, what does this summation of from n equals 1 to infinity of an equals 3 mean? Remember, this is a series. That's a sequence. And let's take a look at the solution. All right, so here is the solution. So part A. So what is a convergent sequence? Well, again, you could just recall from my earlier video. So again, we're reviewing basically all my earlier videos on this. So there's a link to the Hive article, which includes the video inside, and the notes. And here I just put a screenshot from my calculus book just because it's a bit more compact and neat. So here's the definition. A sequence an, right here, is a sequence, just a list of numbers, has the limit L, and we write limit as n approaches infinity of an equals L, or an approaches L as n approaches infinity. And if we make the terms an as close to L as we like, if we can make the terms an as close to L as we like by taking n sufficiently large, get it, yeah, basically infinity. And then, yeah, that's what you write it like here. It has a limit. So if a limit as n approaches infinity of an exists, so it actually approaches a number L, we say the sequence converges or is convergent. So that is basically what a convergent sequence is. It converges to the number L. So we can make n as large as we want, and then an will just approach L. If it does, if the limit does exist, then it converges. Otherwise, we say that the sequence diverges or is divergent if it goes to infinity, or even alternates between positive and negative. You have a number that's not approaching 0. So if it goes to -1 + 1, -1 + 1, again, that's divergent, but it's not going to infinity. Anyways, here's the following graphs show sequences that converge to the limit L. So if you have here again, the sequence is just a list of numbers. So if something goes like this, and there's L, and it goes as you go to infinity, it's approaching all the way to this limit. And you could also go up and lower it as long as you're going smaller and smaller and smaller to it. So there's the limit. So that's a convergent sequence. Again, just series, a list of numbers. So now let's look at part B. Part B is what is the convergent series? Remember, a series is summation of them. These are just the list of the numbers. Now if you're actually summing them up. So recall from my earlier video, here this one is on infinite series right here. This video was on infinite sequences. This one's on infinite series. So here's definition. So given a series, and the summation n equals 1 to infinity of an equals a1 plus a2 plus a3, etc. So remember, you're adding as opposed to just the terms a1, a2, a3. Let Sn denote its nth partial sum. Yeah, so that's what you have. If you have Sn, this just equals to the summation from I equals 1 to n, so a of ai, equals a1 plus a2 all the way to an. If the sequence Sn, so now the sequence of the partial sums, is convergent, and limit as n approaches infinity of Sn equals s exists as a real number. So basically instead of doing the limit of the sequence of just the numbers, now you're going to look at the sequence, the limit of the sequence of the partial sums of these numbers. And then basically the limit n as approaches infinity of Sn equals s exists as a real number. In other words, the limit exists. Then the series, the summation of an is called convergent, and we write a plus 1 plus a1 plus a2 plus etc. all the way plus an, and plus all the way to a infinity equals s. So it has a limit. Or the summation from n equals 1 to infinity of an equals s. So basically, if this limit is approaching this, if the summation is approaching the limit, this one is just the limit of this number, of this sequence. This one is the limit of the summation of the sequence, so that's a series. So the number s is called the sum of the series. Otherwise, a series is called divergent if it doesn't approach a number. So yeah, so that is a convergent series. And now let's look at part C. What does limit as n approaches infinity of an equals 3 means? Let's go over here, part C. So what this means is the terms of the sequence, an approach 3 as n becomes large. Yeah, so as n approaches large here, this is an is approaching 3. That's the limit. So again, it's just something like that. So this is 3, then as it's getting large, it's approaching it. And then now if we look at this one here, what does this summation of from n equals 1 to infinity of an equals 3 mean? So now the summation of the terms is approaching 3. So by adding sufficiently many terms of the series, we can make the partial sums as close to 3 as we like. So now, again, the series, we're a convergent series, we're dealing with partial sums approaching a limit. And then the sequence, we're just dealing with the number itself approaching 3, or the list of numbers that sequence is approaching 3. Anyways, let's continue further, and now let's look at question 2. Question 2 says, what is a bounded sequence, and what is a monotonic sequence? And then C is, what can you say about a bounded monotonic sequence? And let's go to the solution. Again, we're dealing, in this case, with the monotonic sequence theorem. Alright, so now let's take a look at the solution. So part A, what is a bounded sequence? So again, recall from my earlier video, this one is, here's a sequence is bounded above. So a definition, a sequence an is bounded above if there's a number capital M such that an is always less than and equal to m for all n is greater than 1. It is bounded below if there is a number lowercase m such that m is always less than or equal to the an terms of the sequence for all n greater than or equal to 1. If it is bounded above and below, then an is a bounded sequence. So that's it's bounded above and bounded below. So the graph below is an example of a bounded sequence, a bounded sequence or a sequence bounded above by capital M or L and bounded below by 0. So if you have L there, or you can just have M here, say an absolute high number, if you haven't solved the limit, and then there's a 0 right here, this one here. So these are the terms of the sequence. They're all between this range. There's capital M and there's a 0. So this is bounded above and below. So that's a bounded sequence. All right, so now let's look at part B. What is a monotonic sequence? Let's go over here. So part B, a sequence is monotonic if it is either increasing or decreasing as per the same video above. So from this link right here, then we have this right here. So definition: a sequence AN is called increasing if AN is less than AN plus 1. So the AN plus 1 is always greater than the previous one. The N plus 1 greater than N. For all N greater than or equal to 1. That is, A1 is less than A2 and less than A3. In other words, A2 is greater than A1, A3 is greater than A2. So you're always increasing the terms like that. And it is called decreasing if AN is greater than AN plus 1. So in other words, the next term is getting is smaller than the previous. So it's getting smaller and smaller. For all N greater than or equal to 1. It is called monotonic if it is either increasing or decreasing. So yes, monotonic is just going the one way, mono. So mono for one direction, one way. It's either increasing or either decreasing. So that is a bounded, and so the part A is bounded, B is monotonic, and now C is, what can you say about a bounded monotonic sequence? And you can recall from the same video above, monotonic sequence theorem, every bounded monotonic sequence is convergent. In other words, for example here, this one is monotonic, it's always increasing. So monotonic, but it has an upper limit. So in other words, it's gonna eventually be less than this. Yeah, it's gonna be less than M. So in other words, you're gonna actually have a limit then. So it's always increasing in this case, but it's always but it's bounded. So in other words, it's obviously convergent. So yes, very, very interesting. So now let's take a look at question 3. So yes, we're basically rapid firing these. Now eventually we get to ones where I actually have to do some solving by using my pen. Like that. Anyways, question 3. What is a geometric series? And then under what circumstances is it convergent? And what is its sum? And then part B, what is a P-series? And then under what circumstances is it convergent? Alright, so now let's take a look at the solution to question 3. So part A, so what is a geometric series? So recall from my earlier video, again, it's the same link as above there. So the geometric series is going to be displayed as like this. So and from summation from n equals 1 to infinity of AR to the power of n minus 1, and this equals to A plus AR squared, and then plus AR cubed, etc. And yeah, so that is a geometric series. And then under what circumstances is it convergent? So it is convergent if this R, this ratio there that you're multiplying every single time, or you're increasing the ratio there, is less than 1. And then it says what is its sum, and its sum is given by right here. So the summation from n equals 1 to infinity of AR to the power of n minus 1 is equal to A minus 1 minus R. I mean A divided by, not minus, A divided by 1 minus R. And this is for R, absolute value of R is less than 1. Yeah, so basically notice here's the first term A, and then you have the ratio there, common ratio. So if the absolute value of R is greater than or equal to 1, the geometric series is divergent. And here's more info. So in words, the sum of a convergent geometric series is the first term A divided by 1 minus the common ratio R here on all these terms there. Even this one, it could be R to the power of 0. And here's a geometric representation, again, hence the word geometric series, is shown below via similar triangles, where S is the sum of the series. So if you have something like this, let's make it bigger. So you have here, so here's a triangle, A, side A here, and then this entire sum is S. And if you go to a side here, so there's an A, and then if you draw a line all the way that's perfectly flat like this to make it a triangle, what you end up having is this side's going to be AR, like that. And then, yeah, such that you'll have, then this one here is going to be AR there. So this ratio is always the same. So if you have AA, the next one's going to be AR. And then this one here is AR squared. So you're always adding an R there, common ratio that basically has exact same angle across here. Yeah, so it ends up being like this. So all these sides AR cubed, etc. And it goes all the way to 0 because it's convergent. So it goes all the way to 0, so you would have it eventually go to the sum S, which is this whole side. Then you could use similar triangles and similar triangles as well. This angle here, yeah, this angle right here is the same as this one right here. Just using our similar triangle setup, because remember, this goes like this and just straight down like that. All it is a Z. These are exactly the same, like that. Alright, so those are the same angle, so then what you could use is similar triangles, so then the ratios are going to be the same. So you can have A, the side, A over A minus R, so this one to this one is equal to this one, this inside one, S to A. Equals S over A, and you could divide by the A everywhere. And this is not AR, this is AR. You can divide by A, you get cancel all that out, you get S is equal to 1 minus, A overall. Let's do it again. I got that mixed up. So again, you have it written right here. Yeah, so the ratio is A over A minus R, AR equals to S over A. Yeah, so S over A and A over A minus R. And now this part right here, I'll just take out the bottom there. So A 1 minus R. So yeah, so now these cancel. You could just multiply it over there and cancel out the same i's there, or you could just have it like this. This and this cancel, so that's 1, and then move this over, that becomes A. So you get S equals 2 A 1 minus R. And that's this part right here. So anyways, I just wanted to illustrate that. And you can see my earlier video to go dive further into this geometric illustration. So anyways, that's part A. Let's look at part B now. Part B, what is a P-series, and then under what circumstances is it convergent? Alright, so let's take a look at the solution there. So part B, so recall from the same video referenced above, the P-series is this right here. So summation from n equals 1 to infinity of 1 divided by n to the power of P. And this is convergent if P is greater than 1, and it's divergent if P is less than or equal to 1. So basically, if this is large like that, for example, 1 over n3, greater than 1, then that's convergent. If it's less, so like, for example, if it's 1 over n, just the power of 1, that is divergent. That's very, very interesting. Now let's continue further. Let's look at question 4. So question 4, yeah, this states, suppose the series, the summation of an equals 3, and Sn is the nth partial sum of the series. What is the limit as n approaches infinity of an? And then what is the limit as n approaches infinity of Sn? Well, if these terms, all these summations approaching 3, this has to be 0. This one is approaching 0. This one right here is partial sum is approaching 3. Well, that's just the partial sum is just the sequence of the summations of this right here. So basically, this is the summation of the terms, or you could write it as a sequence of partial sums. So yes, it's the same thing. So that should be 3. So let's just take a look at the solution. Yeah, so as I stated, so if the summation of an equals to 3, so this series, this just means n equals 1 or n equals 0 to infinity equals the summation of an equals to 3, then the limit as n approaches infinity of an is approaching 0, and limit as n approaches infinity of Sn equals to 3. So again, this partial sum thing just means the same thing here, the summation's there. But you're looking at the partial sum set of infinity, you're going to, for example, sum the 3 terms, the first 3 terms, the first 300, etc. Anyways, continue further now. So question 5 state the following: the test for divergence. That's part A. Part B, the integral test. Part C, the comparison test. And then D, the limit comparison test. And then E, the alternating series test. Then F, the ratio test. And then G, the root test. Alright, so let's take a look at the solution of this question 5. So part A is a test for divergence. And so recall from the same video above, this is all from the series video right here. So whenever I say look at the one above, it's basically the last link. Alright, let's go here. So from the same video above, the test for divergence, right here. So if limit as n approaches infinity of an does not exist, so if the limit of the sequence does not exist, or if the limit of the sequence an is equal to and is not equal to 0, then the series of the summation of the sequence terms, so from n equals 1 to infinity of an, is divergent. So that's the test. So if the limit of the sequence does not exist, or it's not equal to 0. If it exists, for example, if the sum is, let's say if the limit is equal to 3, then you can be summing 3 to infinity. In other words, you're going to infinity. So you need to approach 0. Okay. So now let's look at part B. Part B is the integral test. So again, recall now from my earlier video. This one here is a different video. So infinite sequence series is the integral test and estimate of sums video. So the integral test. So suppose f is a continuous positive decreasing function. So it's a positive decreasing and it's continuous on the interval from 1 to infinity. And let an, these sequence an equals to this function f of n. Then the series of the summation from n equals 1 to infinity of an is convergent if and only if the improper integral, integral from 1 to infinity is improper because there's an infinity symbol there, of f of x dx is convergent. In other words, if these terms right here, if you could write these terms as a function, then the limit of that function from 1 to infinity of f of x dx is convergent. Then the series of the terms is convergent, so n equals 1 to infinity. If it's not, so if the integral from 1 to infinity of f of x dx is divergent, then the series is divergent. So the series from n equals 1 to infinity of an is divergent. Yes, very, very interesting. And again, f has to be continuous and positive and decreasing right there. Basically, the way it looks looking at it is if you have a function like this. A function like this is f of x, and this is x like that. So if it goes like this, if you can, if this is converging, instead of going to infinity, so if this area under the curve is converging, for example, if it goes all the way to 0, like that, and then basically what you gotta look at is the series. The series are going to be the actual summation of the terms, like that. It's going to look something like this, like that. So yes, very, very interesting. Because remember, series, you're looking at discrete values. This one is continuous values, or infinitely small discrete values. Yes, very, very interesting. So now let's look at part C, and part C is the comparison test. So recall from my earlier videos, a different video. So this is the series, this is a comparison test. So the comparison test, suppose that the series summation of an and the summation of bn, so these are series with positive terms. If the summation of bn is convergent, and an is less than or equal to bn for all n. So these terms are always smaller than this one, and this bn is a series convergent. The sequence terms are smaller for an. Then the summation an is also convergent. So you're comparing it with this one here. But if this is divergent, if the summation of bn is divergent and an terms are all greater than the bn for all n, then the summation of an is also divergent, because, well, the terms are bigger than this one, and this one is divergent. And then for part A, for part I, the terms are smaller of a convergent series, so that would be convergent. All right, let's look at part D. Part D is going to be the limit comparison test, and afterwards alternating series, the ratio, and root test. So let's take a look at this. The limit comparison test, those recall from the same video above. So in other words, these comparison tests right there, the video. So the limit comparison test, so suppose that the summation of an and the summation of bn are series with positive terms. All right, so those are positive terms. So if the limit as n approaches infinity of an over bn is equal to a number c, where c is a finite number and c is greater than 0, then either both series converge or both diverge. Now that's a very interesting step. Basically, it's like a multiple of each other, so they're just copying each other. So this converges, the other one converges if it's a number here that's greater than 0. And then part E is that alternating series test. So recall from my earlier video. Here's this from this different video. So this is the series. This is the alternating series test right there. So the alternating series test. If the alternating series, and this series right here. So from n, the summation from n equals 1 to infinity of this -1 to the power of n minus 1, so that it's always going to be alternating for positive and negative. So if you put in n equals 1, that'll be 1 minus 1 is 0. So -1 to the power of 0 is 1. You put in 2, that'll be 2 minus 1 is 1. So -1 to the power of 1 is -1. So and then this is bn. So you're going to have something like this: b1 minus b2 plus b3 but minus b4, etc. Plus minus, etc. and where Bn in this case is greater than 0, just so that all the negative size is based upon this term only. It's right here. And so so if this series satisfies I, which is Bn plus 1 is less than or equal to Bn for all n, in other words, it is decreasing. So this one, B3 is less than B2, and then B4 is less than B3, so it's basically decreasing, like that. For all n, and the limit of as n approaches infinity of Bn is equal to 0, so this approaching 0, then the series is convergent, and you can see this visually. Yeah, so if it's if the limit is approaching 0, and if it's always decreasing. So for example, if you start off with 0 right here, so now if you have B1 here, that's this term right here, so B1. Let's say it's this size and it's also positive, so the first partial sum is S1 right here. And now you're going to be subtracting by a number smaller than B1, so you're going to subtract by B2, so then you're going to go backwards now. You're going to go all the way backwards here, so the partial sum is going to be S2, which is smaller than S1. So S2 less than S1. And now you're going to be adding by a number that is going to be smaller than B3. So for example, all the way across here. Now you're going to have this one right here. S3 right there is greater than S2, but it's less than S1 there, because you're always going to be smaller and smaller. And then if you go backwards now, you're going to be subtracting by a number smaller than B3. You're going to go all the way across here, and then you're always going to keep getting smaller and smaller. And then it goes back across here, and eventually you're going to go back all the way to this S value as B is approaching 0. So that's how you visually can see that alternating series test right there. And now part F is the ratio test, part G is going to be the root test. So let's take a look right here. So from recall from earlier videos, this is on the ratio/root test. So the ratio test, if the limit of as n approaches infinity of the absolute value of an plus 1 divided by an is equal to L, so it exists, and it's less than 1, then the series summation from n equals 1 to infinity of an is absolutely convergent and therefore convergent. That's the absolute convergence theorem. And if it's L is greater than 1, so that if the limit as n approaches infinity of this ratio, the absolute value of an plus 1 divided by an is equal to L greater than 1, or the limit as n approaches infinity of an plus 1 divided by an is equal to infinity, so both of them are still going to be greater than 1. Then the series, the summation from n equals 1 to infinity of an is divergent. And lastly, part III, or part 3 of this ratio test. So if the limit is equal to 1 of the from n as n approaches infinity of absolute value of an plus 1 over an, so the ratio test is inconclusive. That is, no conclusion could be drawn about the convergence or divergence of the summation of an. So that's series right there. So if it's equal to 1, we can't use it. Going further, so part G. Part G is the root test. So recall from the same video above, this link right there. The root test. If the integral, right here is part I. Yeah, so if the limit as n approaches infinity of the square root, nth root, not square root, so nth root of absolute value of an is equal to L, and that's less than 1, then the series, the summation from n equals 1 to infinity of an is absolutely convergent and therefore convergent. So if it's absolute, using absolute values converges, it's the same as then that means it's also converging without the absolute value. So II part 2. So if limit as n approaches infinity of this nth root of absolute value of an is equal to L, is greater than 1, or if the limit is goes to infinity, so does not exist right there, then the series summation from n equals 1 to infinity of an is divergent. And then part 3, if this limit of as n approaches infinity of the nth root of absolute value of an is equal to 1, the root test is inconclusive, similar to the ratio test, like that. Alright, so that was a good review of those tests. So now let's take a look at question 6. This states, what is an absolutely convergent series? And then part B, what can you say about such a series? And then C, what is a conditionally convergent series? Alright, so let's take a look at the solution. Again, rapid firing these right here. So solution part A, what is an absolutely convergent series? So recall from the same video above, over here, this link right here, is absolute convergence in the ratio root test. So the definition right here. So a series the series from summation of an is called absolutely convergent if the series of absolute values, which is the summation of absolute value of an, all the terms are going to take the absolute value, is convergent. So there's always positive values there. So if it's absolutely convergent, if this series is convergent using the absolute values. And part B, what can you say about such a series? So again, recall from the same video. The theorem, if a series, the summation of an is absolutely convergent, then it is convergent without the absolute values. So this is convergent, this absolute values, then this is also convergent. So part C is, what is a conditionally convergent series? So recall from the same video above, definition. A series, summation of an is called conditionally convergent if it is convergent but not absolutely convergent. And usually what this means is you're going to have a bunch of positive and negatives cancel out. But if you took the absolute values, they would be not canceling out. So you just go to, it would diverge otherwise. So so conditionally convergent is if converges, but not absolutely. They're very interesting. So now let's take a look at question 7. All right, so question 7, part A, if a series is convergent by the integral test, how do you estimate its sum? If a series is convergent by the comparison test, how do you estimate its sum? And if a series is convergent by the alternating series test, how do you estimate its sum? All right, so now let's take a look at the solution, and let's look at part A first, and that is dealing with the integral test. So it's a convergent series by integral test, and we're asked how do you estimate its sum. So part A, we can use the steps and formula from my earlier videos. This is on the integral test and estimate of sums. And first, recap on the integral test. So suppose f is a continuous positive and decreasing function on the interval from 1. This square bracket means includes 1 up to infinity, and that's where this non-square bracket, regular bracket, means it's not actually gonna hit the infinity because it's infinity. And let an equals f of n. So you could write the terms as a function. Then the series, the summation from n equals 1 to infinity of an, is convergent if and only if the improper integral, the integral from 1 to infinity of fx dx, is convergent. It's improper because there's infinity signs, so you have to take a limit and so on. In other words, so if the integral from 1 to infinity of fx dx is convergent, then the series from the summation from n equals 1 to infinity of an is convergent. And likewise, if this integral is divergent, then the series is divergent. Again, this is based on writing an as a function f. All right, so to estimate the sum, we first need to estimate the size of the remainder. So Rn equals to S minus Sn, and this Rn is the remainder. S is the actual sum, the convergent sum of the infinite series, and Sn is the nth partial sum. And when you subtract this, what you're going to get is just this an plus 1, plus an plus 2, plus an plus 3, plus etc. So this is what remains. And we could see that by first noting that the terms an plus 1, an plus 2, an plus 3, etc. are all the terms that remain, since S is the infinite convergent sum of terms, while Sn is just a partial sum up to n terms. So let's just write this down to illustrate this. So if you have S minus Sn, this equals to, well, this is just the full, S is the actual series, or the sum of the series. So we're going to have A1 plus A2, and it keeps going on, dot, 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 and includes AN, and it's going to get AN plus 2, plus dot, dot, dot. It goes to infinity over there. And now we're going to subtract this by the nth partial sum. So this one's going to infinity, but now this AN, this Sn is just going to go up to n only. So A1 plus A2 plus dot, dot, dot gets over to this AN, and that's it, because it's the partial Sn partial sum right there. So this full thing is the full sum. This one is the partial sum. So then what's going to happen is everything that remains afterwards is the Rn remainder. So that's what remainders. Once you subtract this, because these all just cancel. So cancel, 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 etc. Cancels, cancels. So that's all that remains. All right, so continuing further. So now, depending on whether we integrate starting from n or n plus 1, we can have have an upper and a lower bound for the remainder. And we're going to be integrating this function right here. Because remember, you need to integrate this by the integral test. So integral from 1 to infinity of fx dx. But in our case, we want to find the remainder. So let's just say we calculate a partial sum. And then we get these terms, an plus 1, an plus 2, etc. So we could just take the integral up to, starting from n as opposed to starting from 1. So if we integrate starting from n, we're going to have the integral is going to be, bigger than the remainder. And you can see this visually. So Rn equals an plus 1 plus an plus 2 plus a sort of ... And this can be less than or equal to the integral from n to infinity of fx dx. And you can see that visually here. So if you have this y-x axis like that. So here's the n value. And this up here is the f of n, like that. Notice how this is greater than our this height over here, which is the an plus 1. Yeah, so this height is over here. Yeah, this value right here is the an plus 1 over here. And this rectangle is just the height of this is just, the width is just going to be n plus 1. So this is n plus 1. They're all going to be just 1. Yeah, this is just 1 because this is n plus 1. So subtract those 2. That's just going to be n plus 1 minus n. They cancel, equals 1. So yes, so all these rectangles, all those are an plus 1. Again, if you multiply by 1, the width is going to still be an plus 1. And this integral, though, is all of it below it. So that includes this extra space. So this whole thing is the integral, not just the square, or not just the rectangle. So that's this whole thing. And you could see that when you start from n, this is going to be greater than this. So right here. So this is greater than or equal to this part right here, equal to the squares. So these are the remainder. All these are the remainder. And there's always these extra gaps. That is, so basically that's the upper limit for our remainder. And this is getting close to our estimating the sum. So that's the upper limit. And now we're going to look at the bottom limit. Yeah, so if we take the integral, instead of taking integral from n, we take integral from n plus 1. And that's starting from here. So in this case, we're going to have Rn equals to an plus 1 plus an plus 2 plus ... And it's going to be greater than or equal to the integral from n plus 1 to infinity of fx dx. Like that. And you can see we're starting from here as opposed to previous one we started from here. Now we're starting from here, and you can see this visually. Again, all the widths are just 1. So this is an plus 1 goes over here, and these are the extra gaps. So this is greater than the fx, greater than this one. So greater than the integral, because the integral is just going to be all of it below here. So you have that extra gap there. So thus the remainder is between two integrals, and here is the remainder estimate for the integral test. So suppose f of k equals to a k, where f is a continuous positive decreasing function for x is greater than or equal to n, and the series, the summation of an is convergent. So if Rn, the remainder, is equal to S minus Sn, then the remainder is going to be between this integral from n to infinity of fx dx, is going to be less than that, and greater than the integral from n plus 1 to infinity of fx dx. Yeah, so that's the remainder. So now we have an upper and lower limit for the remainder. So thus, likewise, the sum can now be estimated as follows. So the sum is going to be the partial sum plus the remainder. And the remainder is going to be, less than or equal to this, using this n over here. So using the upper bound for the Rn. And this is, again, Rn upper bound. And then it's going to be greater than or equal to just partial sum plus the lower bound. This Rn there. This is the lower bound right there. From integral from n plus 1 to infinity of fx dx. So there is, we can estimate the sum of the infinite series that was convergent by the integral test. And all we gotta do is just solve Sn at any point. Then we could just take the integrals and see the how close it is to the actual sum. All right, so now let's take a look at part B, and let's scroll up to part B. So part B, if a series is convergent by the comparison test, how do you estimate its sum. So let's take a look at this. So we can estimate the sum using the remainder estimate of the convergent series being compared. And such as in the example from my earlier video, and here's a link to it. And yes, we'll go over this, and it has an example on that. So this is from the comparison test earlier video. So the comparison test, again, recap on it. Suppose that the series summation of an and this series bn are series with positive terms. So summation of bn there. You have basically two cases. If I, or part I or part 1, if the series bn is convergent and an terms are all less than or equal to bn for all n, then the summation an is also convergent. If this series bn is divergent and an is greater than or equal to bn for all n, then the series an is also divergent. Alright, so now here is an example from my earlier video, example 5, that I went over and estimated the sum using the comparison test. So use the sum of the first 100 terms to approximate the sum of the series. Right here is the summation of 1 divided by n cubed plus 1, and estimate the error involved in this approximation. So we have this one here, and we're going to compare it to this right here. This is just a p series. And this is convergent because p is greater than 1 there. So this is 1. So basically 1 divided by n cubed plus 1 is less than 1 divided by n cubed because you have this extra 1 there. You're dividing by a bigger number at all times. And note that 1 divided by n cubed is a convergent p series. Alright, so since the terms right here are smaller than this comparison one, the given series is convergent by the comparison test. And the remainder Tn for the comparison test, for the comparison test series, or not comparison test, so it's going back here, so the remainder Tn for the comparison series, this right here, we had the remainder already, was estimated in example 5 in section 11.3, as again, earlier video. We'll go over that in a bit here, that's this one right here. Yeah, we'll go over this later after I cover this example, and again, that one used the remainder estimate for the integral test that I just went over in part A. So basically used estimate like that. Yeah, so there we found in section 11.3, we found that the remainder is less than this integral from n to infinity of 1 over x to the 3. And again, identical to this right here. Yeah, this remainder is less than this part right there. And yeah, so this integral right there is just equal to 1 divided by 2 n squared. And yeah, this 1 over 2n squared, we could just see that from the, again, earlier video here. So for reference, here's integral from the example referenced above. And this was from the integral test and estimate of sums video. So we were asked to approximate the sum of the series, the summation of 1 divided by n cubed by using the sum of the first 10 terms, etc. And I'm just going to look at that integral. So that's what we used right here. And here's that integral right here. So in both parts A and B, we need to know the integral from n to infinity of fx dx with fx equals to 1 over x cubed, which satisfies the conditions of the integral test. We have so integral from n to infinity of 1 over x cubed dx equals 2 limit. As t approaches infinity, just change the variable just for the limit here. So integral of this, remember this is equal to x3 and x to negative 3, so you have to add a power to it. So this becomes x to the negative 2 because you're adding plus 1 to it. And then you put a negative, then divide this by negative 2 like that. Just remember the integral rule and then carry it down. And now you plug in this n and t, and the t is just because you can't put infinity in there, so you're going to take a limit. So you're going to get this right here, and then you're going to evaluate it from n to t. So then when you put in, yeah, it's going to be t right here, subtracted by this, so subtracted by a negative, becomes a positive over here, and then you plug in infinity, this goes to 0. This goes to 1 over infinity, goes to 0, and you end up with 1 over 2n squared. Anyways, just going over that. So that was the integral that was used there. So the remainder is less than this for the comparison. So therefore, the remainder Rn for the given series, this one here, is going to be less than the remainder Yeah, less than the remainder of the comparison one. So this right here is less than this right here, and that's because the comparison test, this is smaller. So this one is convergent, but all of these terms are smaller, so this is also convergent. So then the remainder is going to be the same, but smaller terms. So every single one's going to be smaller. So there is how we could use the estimate setup there. Yeah, so this means here, so with n equals to 100, if you plug that into Rn, it's going to be, well, or in this one right here, you get this 0.00 with 4 zeros and a 5. So 0.00005. So the remainder at the 100th n, or the remainder of the 100th partial sum is equal to this right here. It is less than that. So using a programmable calculator or computer, we find that the summation from n equals 1 to infinity of 1 divided by n cubed plus 1 is approximately equal to, and here just plug in up to 100. So we're going to go to, this is S 100. This is S, but it's approximately equal to it because the remainder is so small. So this means that this is going to be equal to approximately 0.6864538 with error less than 0.00005. So that's an estimate. So that was the example we went over. Now part C. So part C is asking if a series is convergent by the alternating series test, how do you estimate its sum? Well, if it's convergent by the alternating series test, this one is more straightforward than the other ones because we don't need to take integral or etc. or compare it. We could just add terms until we reach a desired accuracy given by the alternating series estimation theorem as stated in my earlier video. Yeah, so we have an alternating series estimation theorem. If S equals to an alternating series, so summation of this -1 to the power of n minus 1, Bn is the sum of an alternating series that satisfies this I, where Bn plus 1 is decreasing, so it's less than or equal to Bn, but it's greater than or equal to 0, so it's always positive. And the limit of Bn is approaching 0 as n approaches infinity. Then the remainder, or the absolute value of the remainder, is equal to the difference between the sum, which is the absolute value of the sum minus partial sum, and it's going to be less than or equal to Bn plus 1. Yes, in other words, we always know the accuracy, so what remains is always going to be less than or equal to this term, so Bn plus 1. So if we want to go R100, the remainder is going to be, well, less than or equal to B101. So we just take the next term, and that's how we can get more accuracy. So we can visualize this theorem from the earlier figure. So if we have 0 right here, here's the first term, B1, goes all the way to S1 as a partial sum. And if you go backwards, we go back to S2, but this absolute value is less than. So this B2 is less than B1, and you're subtracting it, so you're going to go over here, less than it. So then the difference between from here and here, this difference, this is going to be our S. It's going to be our S minus Sn, because this is this right here. Yeah, this part right here. I'll just put a space here. From here to here is our S2. From here to here is our S. The actual sum of the infinite series is this S1 right there. So when you subtract it, you get this remainder here, R, like that. And this value right here, so this remainder S minus Sn is always going to be less than the next term. So now if you have this plus 3 right here, so that this one goes all the way across here, now you have this S3. So this is, from here to here is B3. So then this is going to be less than or equal to B3. So that's our size. And then if we go backwards now, so now you go backwards again. So from here you go to negative B4, so all the way up to here. So if we start all the way up to there now, that means this is going to be our remainder, S minus S4. So that this is R4. And then the difference, now this is going to be, well, less than this B5 is you're going to go across it all the way there. So you're always going to go, this is B5 there. So because the S is going to be in the center over there. And this is going to be B5. B5. Yeah, so it's going to be less than that setup over there. And this is going to be less than or equal to B5. It's fascinating stuff there. So that's how it is. You can just keep adding the terms and you always know the error. The error is always going to be the next term right here, Bn plus 1. So that's how big it is. So you can just keep adding. So notice that S minus S4 is less than B5, and S minus S5 is less than B6. So this is the S minus S5. The absolute value here is less than this right here. Less than this section there. So it's fascinating stuff. All right, so now let's look at question 8. And question 8 states, write the general form of a power series. And then part B says, what is the radius of convergence of a power series? And then part C, what is the interval of convergence of a power series? All right, so now let's take a look at the solution. So let's look at part A. So this is the general form of a power series. So recall the general form of a power series from my earlier videos. Here's the power series link there. So here's just the general form. So this is summation from n equals 0 up to infinity of Cn times x minus a power of n. So it's, there's coefficients there. And you're going to have this C0 plus C1, etc., C2, and then you can multiply in this side here. So we're going to have, just say the whole terms again. So C0 plus C1 times x minus a plus C2 times x minus a squared, and then it goes to C3 times x minus a cubed, and so on. So that's the general form of a power series. So again, you're taking to the power of that there. And now B, what is the radius of convergence of a power series? So part B, recall the radius of convergence from the above video. So this one right here. And I'll just make this bigger here. So just read up all on these notes here. So theorem, for a given power series, summation from n equals 0 to infinity of Cn times x minus a to the power of n, there are only 3 possibilities. So that either the series converges only when x equals to a, the series converges for all x, or 3, there is a positive number r such that the series converges if absolute value of x minus a is less than r, and diverges if absolute value of x minus a is greater than r. And this number r in case 3 is called the radius of convergence. So that's the radius of convergence right there of the power series. It's where it's basically where the series converges. It's that interval where it converges. By convention, the radius of convergence is r equals to 0 for this case, if it's only at x equals 1, so it would be 0 radius, just r equals 0. And if if it converges for all x, that radius would be infinity, so r equals infinity in case I, or case 2. The interval of convergence, we'll get to that in a bit, or actually I'll go over it now as well as just recall. So this is part C. What is the interval of convergence of a power series? So that's right here in this write-up. The interval of convergence of a power series is the interval that consists of all values of x for which the series converges. In case I, the interval consists of just a single point A. In case II, the interval is from negative infinity to infinity. That's for all x. In case III, or part in case 3, note that the inequality x minus a less than r can be rewritten as, if we remove that absolute value, you can have it as x is greater than a minus r, or x is less than a plus r. And the reason you can rewrite this inequality is absolute value x minus a is less than r as this. This inequality just means that, well, what you have is x minus a is going to be less than the positive r, and it's going to be greater than the negative of this r. Because remember here, when it's in between here, this absolute value is going to be less than absolute value of r there. For example, negative 3 is less than 2. But absolute value of negative 3 is equal to 3, which is greater than 2. So in both cases, you have r is greater than it. So yeah, this is just a little refresher on inequalities. And then what you could do here is add plus a to all sides in the middle, and plus over here. So then this just cancels. So now you're left with this inequality. X is less than r plus a, or a plus r, and x is greater than a minus r. So yeah. All right. Alright, so now that we've written that, so note further, so when x is an endpoint of the interval, that is when x is equal to a plus or minus r. So when x is either one of these, anything can happen. The series might converge at at one or both endpoints, or it might diverge at both endpoints. Thus, in case 3 right here, there are 4 possibilities for the interval of convergence. And here is these points right here, and we'll show you the illustration of it here. So you have 4 different cases. You have A minus R and A plus R. This is the regular bracket, so it does not include these endpoints. So you could have the point with a non-shaded circle like that, and this point like that. And then you could have this one A minus R, so it doesn't include that, and then this other one includes that point, so make it like that. And you can have this interval right here. So this is an open interval, this is closed, and here's a closed interval, A minus R, so at the endpoints as well it converges, and is A plus R at the endpoint doesn't converge. And you could also have it at both. So you could have something like this at both. So at this closed interval, a square bracket A minus R, and up to A plus R there, in that radius of convergence there. And the situation is illustrated in figure 3, or this figure right here. So if you have this here centered about A, yeah, so you either have it's only at A that it converges, only at A, all values, or you can have it at this point where convergence for absolute value of x minus A is less than R, where from here to here is R, and from here to here is R as well. And then so on the left side is A minus R, the right side is A plus R. And then you have divergence is when absolute value of x minus A is greater than R. So past this point right here, this point and this point here, the absolute value of it is over there. And this axis, that's the x-axis there. All right, now to summarize, well, before that, let's just go look at that question again. So the question was just asking what is the radius of convergence of a power series, and it's basically where it's where the series converges, and it's this number R right there. And you have 3 cases. You have R is 0 by default, just by definition R is 0 for this case I. R is infinity for this case 2, and then R is this number. The absolute value is less than R if it converges there, and diverges when it's greater than the absolute value of x minus A is greater than R. So yes, to summarize, the radius of convergence is equals 0 if the series converges only when x equals A, is infinity if the series converges for all x, and is a positive number R such that the series converges for absolute value of x minus A is less than R, and diverges for x minus A, absolute value of x minus A is greater than R. And just to make this appear better, I'm going to write for. Actually, that doesn't help either. Or I'll just write for the case. Just so that this doesn't get split into this new line there. So this just for the case absolute value of x minus A is greater than R. All right, very interesting. And now let's look at part C again. Part C was about the interval of convergence. So what is the interval of convergence of a power series? So we went over that. That's just all the values in that interval for which the series converges. And it's this setup over there. But let's just go over further. This is from the solutions manual. Alright, so as stated above, the interval of convergence of a power series is the interval that consists of all values of x for which the series converges. Corresponding to the cases in part B, the interval of convergence is, so if you look at these cases right here, or these cases right here, so you have these cases. Yes, you have either the single point, so for I, you have the single point A right there, so you can call that the interval of convergence. Just put this A with this squiggly bracket. Or you can have the case 2, all real numbers, that is a real number line from negative infinity to positive infinity. And then you have the case 3 is an interval with endpoints A minus R and A plus R, which can contain neither, either, or both of the endpoints. So then this either is either one of them or the other one, so that you'll have 4 different intervals. So 4 possibilities, these ones right here. And going further, so in case 3, or case I, we must test the series for convergence at each endpoint to determine the interval of convergence. So we need to actually test out directly at those endpoints. Yeah, because the radius of convergence just says it converges within that radius, but at the actual radius point, you have to test that separately. And again, it depends on which series you're looking at. Alright, so now let's go further and look at question 9. And this states, suppose f of x is the sum of a power series with radius of convergence r. And then part A, we're asked, how do you differentiate f? And what is the radius of convergence of the series for f prime, or the derivative of f? And then B, how do you integrate f? And then we're asked, what is the radius of convergence of the series for the integral f of x dx? Alright, so now let's take a look at the solution. And here, so we're going to look at derivative. Basically, you're differentiating or integrating the power series. So that's what we're looking at. And so the solution for both parts A and B, recall from my earlier video. And this is representations of functions as power series. And here is that differentiating theorem and integrating theorem. So this applies for both, because you have the first one is derivative, second one is integral. So if the power series, written in general form, summation of Cn, C subscript n, times x minus a to the power of n has radius of convergence r greater than 0, so that's it has a radius of convergence, then the function f defined by f of x equals to c0 plus c1 times x minus a plus c2 x minus a squared plus etc. equals this right here. This is just a power series, so summation from n equals 0 to infinity of Cn x minus a to the power of n is differentiable and therefore continuous. Yes, you can take the derivative and it's continuous on the interval a minus r to a plus r is open bracket, because it doesn't have to be continuous or differentiable at the endpoints, but as long as in between that it does. So yeah, this may or may not be continuous at the endpoints or differentiable, but at the in between it is. And what we'll have is, so here's the theorem. So if you have the power series and this radius of convergence r, and then the derivative is just equal to f prime of x equals to c1. So this one goes to 0. This goes to 0. Yeah, here, pen's working now. So this goes to 0 when you take the derivative, because it's just a constant. And now this part right here, c1 x minus a, derivative of x is just 1. And in this case, derivative of x minus a is also just 1. So then this would vanish. All you're left with is c1 there. And now this one here, derivative here, the 2 goes down, and then then this becomes a 1. So this becomes here. The 2 goes down here, c2 x minus a power of 1. Likewise, in x1, the 3 goes down, and then this subtracts a power, goes to 2, and you have the c3x minus a, etc. And this is equal to, and you can see the derivative here, so this n goes down, you subtract 1. So this is the summation n equals 0 from n equals 0 to infinity of Cn x minus a to the power of n. And now this becomes over here, it just becomes the summation from n equals 1 up to infinity of n Cn x minus a to the power of n minus 1. Again, just a basic derivative rule. This goes down, the n goes down, subtract by 1. And we start from n equals 1 because, well, n equals 0 is vanished, so you could just ignore that. You could even put n equals 0, doesn't change anything. Except, actually, no, if you put n equals 0, then this would be a negative power. So that's this is actually n equals 1 to match up with this. So that this is n minus 1. 1 minus 1 is power of 0. So this would be x minus a to the power of 0, which equals 1 over there. Alright, so that is a derivative, and yeah, so that is how you differentiate it. You can just differentiate it just like a typical function, so the terms inside differentiate. And likewise, the integral, you can also do the same thing. Yeah, so if this is a function, if you take the integral of it, if you take the integral right here, so c1 is a constant, the integral of that, actually no, not c1, we're dealing with this, not this one. But that's a derivative, so c0 integral of that, yeah, that's just going to be, well, you add c0 is going to be x there, then plus a constant c. But this, they've rewritten it like this, and I'll get to that in a bit. I'll also just show that right here. So in part II, the integral of c0 dx is equal to c0x. Yeah, so integral of constant goes to x. And then plus an extra constant, they'll call it c1, is written as, so they wrote it like this. Yeah, so they wrote it as this c plus c0 times x minus a. So yeah, there's a plus c there. Where the c without the subscript is equal to c1 plus a c0. And again, these are just a constant. So just writing the constant in this way as a function of the C0 there. And this is just so all the terms of the series have the same form, so that you write it as a C0 x minus a. So anyway, so that's the that term. Then the next ones are pretty straightforward. So you have the C1 times x minus a. So the integral goes to a 2, then divide by 2. There's a 2, and there's divide by 2. The next one's going to be, this would be a 3 divided by 3, like that. Again, just remembering the integral rules there. So then what this ends up being, if you write it in this formula form, equals to c plus the summation from n equals 0 to infinity of cn, and then x minus a to the power of n plus 1, and then divided by n plus 1. Yeah, so if this is n right here, and then this would be n plus 1, then divided by, then this would go to n plus 1, divided by n plus 1. When you take the integral, and you do this for all the term. And the 0 is C0 there. When you plug in n is 0, that just goes to 1 and divided by 1. And in both cases, you're asked for the radius of convergence for the derivative and the integral. Recall that the radii of convergence of the power series in equations 1 and 2 are both r. So they're both the same. So they don't actually change. So it's the same as the function f, like that. Very interesting. And yeah, that's this form right here. This is just taking the integral and derivative, but in more generally. So note 1, equations 1 and 2 in theorem can be rewritten in this form, just so it's more straightforward as opposed to actually evaluating this integral. So this part that you could write this as a formula 3. So d over dx of, so derivative of the series, of the power series, summation from n equals 0 to infinity of cn x minus a to the power of n is equal to the derivative inside, like that. Yeah, so the derivative of the series is equal to the summation of the derivative of every single term. So d over dx of the terms inside cn x minus a to the power of n. And likewise, the integral of the entire series, the integral of the summation from n equals 0 to infinity of cn times x minus a to the power of n dx is equal to the summation from n equals 0 to infinity of the integral of every single term. So the integral of cn x minus a to the power of n dx. So yes, very, very fascinating stuff like that. And just for reference and for recap on that earlier video. So we know that, here's some more notes. So we know that for finite sums, the derivative of a sum is the sum of the derivatives, and the integral of a sum is the sum of integrals. Equations 3 and 4 assert that the same is true for infinite sums. So this one's usually the case for regular finite sums, but now we're looking at infinite sums. So the same as, so these equations assert that is true for infinite sums, provided we are dealing with a power series. For other types of series of functions, the situation is not as simple, and this is exercise 36. I believe I went over that in this video. And note 2, although theorem 2, this theorem 2 right there, states that the radius of convergence remains the same when a power series is differentiated or integrated, this does not mean that the interval of convergence remains the same. Remember, at the endpoints, it could be an open or closed bracket, so the endpoints may not be. So it may happen that the original series converges at an endpoint, whereas the differentiated series diverges there. So that's the exercise 37. And another note here, note 3, the idea of differentiating a power series term by term is the basis for a powerful method for solving differential equations. We will discuss this in method this method in chapter 17, or in this case a later video, which will be on second order differential equations, and I'll be in the future. Hopefully we get to that soon. Alright, so that is basically the integrating and differentiating power series. And now let's look at question 10, and this states, write an expression for the nth degree Taylor polynomial of f centered at a. And then B states, write an expression for the Taylor series of f centered at a. So this is the nth degree Taylor polynomial. Now we're looking at the Taylor series. This is summation up to infinity. And then it says, write an expression for the Maclaurin series of f. And then D states, how do you show that f of x is equal to the sum of its Taylor series? And then part E state, it says state Taylor's inequality. Alright, so now let's take a look at the solution. So let's look at part A. This is right expression for the nth degree Taylor polynomial of f centered at A. So part A, recall from my earlier video. This is on Taylor and Maclaurin series. And so what we have here is the nth degree Taylor polynomial. So t sub n of x is equal to the summation, I'll make this bigger, summation from I equals 0 to n of the ith derivative at A or of A divided by I factorial times it by x to the x minus A to the power of I. So when you plug in 0 there, that's just the 0th derivative, in other words, just a function. So f of 0 is just a function, not the derivative, of A divided by I 1 factorial, or 0 factorial is just 1. And then the power of this is x minus A, the power of 0, that's just 1. So that's just f of A. The next one's going to be f first derivative at A divided by 1 factorial, then times x minus A power of 1. The next one's second derivative. Now you have a 2, and the third one's then go all the way to the nth derivative divided by n factorial times x minus A power of n. Yeah, so that is the nth degree Taylor polynomial of f centered at A. So centered at A, that's how you would write it like that. Hence, when you're dealing with radius of convergence, you're centered about that A point, A, and then you're centered, and then it's the radius is outwards, like a circle of convergence there. So hence the phrase centered. So now let's look at part B. It says write an expression for the Taylor series of f centered at A. Alright, so part B, recall from the same video above. This is the nth degree, but now the series, instead of going to n, we just go straight to infinity. Yeah, so then because there's infinity there, and this one is n is equal to 0, we don't need to write I. It doesn't go up to n there. We just write n equals 0, so just better, it's easier to write because you're not putting infinity in these terms. So summation from n equals 0 to infinity of f of nth degree, nth derivative of A divided by n factorial of, this is the nth derivative of f at A, and then times it by x minus A to the power of n. And then this becomes f of A plus f prime of A divided by 1 factorial times x minus A, then the f second derivative, f double prime at A times by x minus A squared, and all divided by 2 factorial. The next one, you have the third derivative, 3 factorial, and it's power of 3, and so on goes all the way to infinity. So whenever you hear the word series, it's infinity. When you have the nth degree, you're just going up to n terms. So it's a partial sum. Alright, so now let's look at part C. Write an expression for the Maclaurin series of f. So part B, recall from the same video above. So this is the Maclaurin one. That's part C right here. So part C, recall from the same video above. So you have the summation from n equals 0 up to infinity of the nth derivative of f at 0. So the only change is A is equal to 0 for the Maclaurin, just a special case. And then divided by n factorial times x power of n. So basically you're going to have f of 0 plus f prime of 0 divided by 1 factorial times x. The next one, f double prime at 0 divided by 2 factorial x squared. So note that the Maclaurin series is just a special case of the Taylor series where A is equal to 0. Yes, and it's used a lot, and it's useful in many areas, so hence given its own name. But they're both Taylor series. So Maclaurin is a special case of Taylor series. Alright, so now D, part D. How do you show that f(x) is equal to the sum of its Taylor series? Let's take a look at D right here. And we can recall from the same video above, and here's the theorem to show that. So if f(x) is equal to the nth degree Taylor polynomial of x plus a remainder, Rn of x, where Tn is the nth degree Taylor polynomial of f at A, and the limit as n approaches infinity of Rn of x is 0, so in other words the remainder goes to 0, for the radius of convergence absolute value of x minus A is less than r, then f is equal to the sum of its Taylor series for the on the interval inside its radius of convergence. So absolute value of x minus A is less than r. So basically we have to show that this remainder goes to 0, and hence f of x is equal to the Taylor series this right here. Because you could write this for most functions, or a lot of functions right here. You could write the Taylor series for it, but to equate this as f(x), you need to make sure the remainder goes to 0. Alright, so now let's look at part E. So part E states Taylor's inequality. So here's Taylor's inequality to find that remainder. So recall from the same video above, part E. So Taylor's inequality, if the absolute value of the nth plus 1 derivative of f at x is less than or equal to capital M for the absolute value of x minus a is less than or equal to d, then the remainder Rn of x of the Taylor series satisfies the inequality. Inequality right here. So Rn of x, the absolute value of the remainder, is less than or equal to m, which is again greater than this n plus 1 derivative, then divided by n plus 1 factorial times by x minus a to the power of n plus 1 for all x minus a is less than or equal to d there. So yes, a pretty big inequality. And in that video, I went over the proof of it, just quite remarkable, or just tedious and so on. But anyways, yeah, so that is set up there. So now let's look at question 11. And question 11 states, write the Maclaurin series and the interval of convergence for each of the following functions. So you have a is equal to 1 divided by 1 minus x. And here I just quickly added letter f. I forgot to add this e there. So anyways, or this tan, this inverse tan of x there. So anyways, so part A is 1 over 1 minus x. Part B is e to the x. C is sine x. D is cos x. And then E is inverse tan of x, or the arctan of x. And then F is ln x. Actually, I typed this wrong. The question was actually ln of 1 plus x. Like that. Yeah, it wasn't just ln x. So it was actually ln 1 plus x. So now let's take a look at the solution. Alright, so the solution is for all parts A to F. So recall from the same video above, and let's see, the furthest link is just right over here. So this Taylor and Maclaurin series. So we're asked for the Maclaurin series, so that's just a Taylor where A is equal to 0. Yes, so notice how all these x minus A is 0, so you just have x there. So yes, that is the Maclaurin series like that. And here's teleported above. So here's the Taylor series, so x minus A. And then the Maclaurin A is equal to 0. So then you'll have x to the power of n as opposed to x minus a to the power of n. Anyways, let's just dive right in. So this is from that same video. And here is part A. This is 1 over 1 minus x. So 1 divided by 1 minus x, the Taylor series, or the Maclaurin series here is from summation from n equals 0 to infinity of xn. So you're going to have, when you plug that in, so when you have n equals 0, so x to the power of 0 is just 1 by definition. And then plus right here, x to the 1 plus x squared, x 3, etc. And then the radius of convergence is 1. Yeah, so x has to be absolute value of it less than 1 there for this radius of convergence there. And now part B is e to the x. So here's e to the x. So e to the x equals to the summation from n equals 0 to infinity of x to the power of n divided by n factorial. So you're going to have 1 plus x divided by 1 factorial plus x squared plus divided by 2 factorial, etc. And the radius of convergence is r is infinity, so converges for all values of x. And now the next one is sine of x. So sine of x is written right here. So summation from n equals 0 to infinity of negative 1 to the power of n times by, then you have x to the power of 2n plus 1 divided by 2n plus 1 factorial. So it looks like this. So it'll look like x minus x cubed over 3 factorial. So it skips 1 each time. So then plus x5 divided by 5 factorial. Then a minus. It's alternating, and you're going by odd powers and odd factorials. All right, and now let's take a look at the cos one. So the cosine x, bar D, that's this right here. So it's again is alternating. So similar to the sine one. So the summation from n equals 0 to up to infinity. And this is a negative 1 to the power of n, so it's alternating series. And then x to the 2n as opposed to this odd 2n plus 1. and then divided by 2n factorial. So you're going to get a 1, so this could be viewed as x to the power of 0 as even, and then subtracted by x squared divided by 2 factorial, then you have a 4, and then 4 here, and it's alternating as well, so minus plus, and so on. And the radius of convergence is also infinity. And now the next one is E is tan, inverse tan of x, or inverse tangent. So you're going to have over here summation from n equals 0 to infinity of negative 1 power of n. And then this is going to be x to the 2n plus 1 divided by 2n plus 1. But it's not factorial. So this is exactly the same as the sign. Notice here's exactly the same. Everything's the same except this is not a factorial. It's not a factorial in there. So there's no factorial there. But those ones are factorials, which is quite interesting. And the radius of convergence for this is 1. So not infinity. These are infinity, this is 1. Alright, then now the next one is ln 1 plus x that we're asked for. This one also has the binomial set up over there. This is 1 plus x power of k. But here we're going to look at this one here. Ln of 1 plus x equals to the summation from n equals 1 to infinity of negative 1 to the power of n minus 1 times x n divided by n. Yeah, so this one is going to be x minus x squared divided by 2 plus x cubed divided by 3 minus x4 divided by 4. So this one doesn't skip any odds or evens. This goes every single term, but it's divided by and it's alternating over there. And the radius of convergence is 1. Alright, and just a note here. So note that the above image includes the power series for ln 1 plus x, which is from the 7th edition of my calculus book, while the 6th, which I used for my previous video, did not have it. So this wasn't in the table right here. This wasn't in that video. But however, I went over ln 1 minus x in a later video. Here's a link to it. So again, there's a power series video. This was part of example 6. Just to illustrate here. So find a power series representation for ln 1 minus x and its radius of convergence. And I showed that going over a bunch of steps here and basically solved it over here. So ln 1 minus x equals to negative x minus x squared divided by 2 minus x cubed divided by 3. So they're minus. So these are all minus. And then it basically equals to negative summation from n equals 1 to infinity of this is going to be xn divided by n, and where the radius of convergence is 1. So absolute value of x is less than 1. Yes, you have r is equal to 1. So that is for 1 minus x. So just for completeness, let's just solve the ln x. So note that we can replace x with negative x in the above ln 1 minus x power series to get the power series for ln 1 plus x. Yeah, so we could basically just manipulate that and get it. So what we'll have is ln of 1 minus, and then this is minus x, so if x is that instead, and we can just plug that inside the power series. Oops. Yeah, so this is going to equal to negative, so this one right here, so negative x, and then we're going to have a negative x squared. If you put a negative inside, that's just going to be positive anyways, so you can just leave that. Or you could just, for completeness, put it in there as well. Negative x squared, and then minus negative x cubed over 3, and then minus plus, dot. So this happens is this one's going to be positive. So it goes positive x. This one is negative x squared. Anytime you have an even power, it doesn't change. It's going to be a negative x squared. It's going to be positive there. So notice these ones are all negative, but now every odd, because you have a negative there, so negative, the power of a odd number there is going to be negative, and then negative times negative is going to be positive. So this becomes positive x3 over 3. And the next one's going to be negative x4 over 4. The next one's going to be plus next one's going to be plus x 5 over 5, etc. And then it's going to be negative plus dot. Yeah, so we have this right here. So it's going to be alternating, and yeah, we could write it as this form over there. This is, yes, notice the exact same thing here. So x minus x squared over 2 plus x cubed over 3 minus x4 over 4. So the evens are negative, the odds are positive. And right here, yeah, notice this becomes, when you put in the negative there, those cancel. That's just the same thing as ln of 1 plus x. So this equals to this over here. And now if you write it as a formula, as a summation formula, we get the summation. Let's write this over here. Summation from n equals 2. Well, let's start. This one has a power of 1. Then let's just start with power of 1 up to infinity of, and then this is going to be, it's alternating. So we're going to have, let's go with -1 to the power of, well, we could just do the same thing as the one listed in the table, so n minus 1. So if you plug in 1, that's going to be power of 0, it's going to be 1. If you plug in 2, it's going to be 2 to the 1, 2 minus 1 is 1, so -1 to the power of 1 is negative. So it's negative and alternates every single time, and then this is going to be xn over n, like that. So there it is. That is our, and I'll put this here for completeness, ln 1 plus x. Like that. There is our formula. And this is double check. So this checks out. It's going to be -1 over here. So yeah, so this is ln 1 plus x is equal to the summation from n equals 1 to infinity of -1 to the power of n minus 1 times xn over n. This equals to, again, x minus x squared over 2 plus x cubed over 3 minus x4 over 4. And radius of convergence is 1. So it's the same thing. Because these are basically the same formulas. We're just switching that variable. Alright, so now let's take a look at question 12. And this one states, write the binomial series expansion of 1 plus x to the power of k, and then is asked what is the radius of convergence of this series. And now we can just dive further into here. So this is the series expansion of 1 plus x, the binomial series 1 plus x to the power of k, and that's actually over here as well in this table. There's a table, but so we could basically see that, as well as in my earlier video over here on the Taylor and Maclaurin series. Actually, this is the same video as this link above here. This one here is the same link. And specifically went over the binomial series in that video. So the binomial series is right here. So if k, and make this a bit bigger, if k is any real number and the absolute value of x is less than 1, which is also the radius of convergence 1. There's the radius of convergence for the binomial series is 1. Then 1 plus x to the power of k equals to the summation from n equals 0 to infinity of this, in the bracket, n choose k. I pronounce k choose n just because this is written on the top, this is the bottom there. Typically it's written other way around, n choose k, like that. But in this case, they just have a k on the top and at the bottom there. And we'll go over that soon. Those are the binomial coefficients. So if k is any real number and absolute value of x is less than 1, then you'll have this. So 1 plus x to the power of k equals to summation from n equals 1 to infinity of k choose n times x to the power of n. And this is going to equal to 1 plus kx plus k times k minus 1 divided by 2 factorial times x squared, plus k times k minus 1 times k minus 2 divided by 3 factorial, and then this is times x cubed plus ... And the radius of convergence for the binomial series is 1. Note that the term in big brackets here is the binomial coefficients, and often pronounced as k choose n. And let's just write the formula for it. So here's the formula for kn, like that. This is equals to, it's equals to k factorial over n factorial times it by k minus n factorial. And now let's just take a look at an example here. If n here equals to 3 right here. All right, so let's take a look at that scenario. So if n equals to 3, then what we'll have is or here I just moved it around to put this arrow there, make it a bit neater. So what we're going to have is k choose 3 is going to equal to k factorial, and then divide this by 3 factorial, that's n, and then k minus 3 factorial, or factorials on the outside. So what this ends up being is, well, let's just expand the k. Let's just say k is any real number, and let's say the factorial expands out like this, k, and then k minus 1, and then the next one's going to be, well, k minus 2, and the next one is going to be k minus 3, and I'm just going to stop there, but write a factorial so that it keeps going on and on. Factorial, so it just keeps going on, and then you're going to divide this by 3 factorial times k minus 3 factorial. So in other words, this and this cancel out. All you're left with is k times k minus 1 times k minus 2 and then divide this by 3 factorial. And if I just box this out, this is exactly what we have right over here. So there's k times k minus 1 times k minus 2 divided by 3 factorial. That's the third coefficient, or the fourth coefficient here, but the x to the power of 3 is coefficient over there. Yeah, or for n equals 3, this is the coefficient when n equals to 3, and then this is the actual first coefficient is 1 there for, well, by itself, for n equals 0. But anyway, so you get this scenario there. So yes, very, very fascinating stuff. All right, and with that, we're done. The concept review or concept check, the review section of the end of the calculus, at the end of the infinite sequences and series calculus chapter. Now let's look at the true or false quiz, also at the end of that chapter. So this is asking, determine whether the statement is true or false, and if it is true, explain why, and if it is false, explain why, or give an example that disproves the statement. All right, so let's take a look at question 1 here. So if the limit as n approaches infinity of an equals to 0, then the summation an is convergent. In this one, it's obviously going to be false, because just because the limit is going to 0 does not mean it is convergent. We'll go over to the solution right here. So solution, this is false. So recall from my earlier video, here it is. This is from the geometric series article / video. And this was the theorem given there. So if the series, the summation from n equals 1 to infinity of an is convergent, then the limit as n approaches infinity of an equals to 0, but not necessarily the other way around. Just because this is convergent, so if this is convergent, then this limit has to go to 0. But if this is going to 0, does not mean it's convergent. So note 2, the converse of theorem 6 is not true in general. If limit as n approaches infinity of an equals 0, we cannot conclude that the summation an is convergent. Observe that for the harmonic series, which is a p series, summation from 1 over n, we have an equals to 1 over n approaches 0 as n approaches infinity. But we showed in example 7 that summation of 1 divided by n is divergent. It's also a p series, and it's a divergent p series. Yeah, and I just added a note here. So note also that the harmonic series, the summation from summation of 1 over n, is a divergent p series, and we could actually have a look at p series right here. And let's go back to it. And yeah, that's right over here. So this was part of question 3. What is a p series, and under what circumstances is it convergent? To recall here, so p series, the summation from n equals 1 to infinity of 1 over n to the power of p, is convergent if p is greater than 1 and divergent if p is less than or equal to 1. And in our case, the harmonic series is less than or equal to 1. And when it's it's equal to 1. So 1 over n goes to 0, the terms, but it's not convergent as per the p series. Let's continue further now. All right, so let's just teleport back here. So yes, it is a p series, and yes, so this statement is false. So that harmonic series, the terms go to 0, but the summation of the terms don't. The summation of the terms don't converge to a single value. They go to infinity. So in other words, it's not a convergent series. So the statement is false. All right, let's continue further. So question 2. And question 2 states the series, the summation from n equals 1 to infinity of n to the power of negative sine of 1 is convergent. And this is an interesting question. This is actually a p series as well. So let's go here. So let's look at the solution. So solution, this is false actually. So note that this is just a p series where p is less than or equal to 1, and you could calculate that. Or first, let's take a look that this is a p series. So you could write this as, so the summation up to infinity from n equals to 1 of n to the power of negative sine 1. This equals 2, and you could invert that power. So get rid of that negative sign from n equals 1 to infinity. This is going to be equal to 1 over n to the positive sine 1. So this is just what this means whenever you have a power, a negative power like that. And so this one right here is just p. So that's just our p. Yes, in other words, this is the equivalent of a p-series from n equals 1 up to 1 over n power of p, where p is equal to sine of 1. So then we need to determine the value of sine 1 and use the p-series test. And so we can just calculate that right here. And here, if you plug in sine 1 to the calculator here, I'll just show you right here. Go like this. So this is my OneNote program that I'm using for these notes. They have a built-in calculator, so I can just press space, and this calculates it as over here. So this is in degrees, though. Let's delete this. So that's in degrees, and you might as well just bold these. I'll bold the calculations setup is over there. Remove this right here. Yeah, so that's in degrees, but almost always, if it's not, unless it's mentioned, it's talking about radians. So you have to convert that into radians. So 1 degree times it by 180 degrees per pi radian. So divide by pi like that, and you're gonna get this answer right here. And you could just have a look right here. So if I press space, it equals to 0.8414, etc. So that is our answer. So this is in radians. Unless otherwise stated, this is usually the case. So P equals to sine 1 is approximately equal to 0.84, which is less than or equal to 1. And the this P series diverges. So this is false. So this is false. It is actually, divergent, not convergent. So it's very interesting. All right, so now let's continue further and look at question 3. So question 3 states, if the limit as n approaches infinity of a(n) equals to L, then the limit as n approaches infinity of a 2n plus 1 equals L. And this is actually pretty straightforward. It's actually true. And this is because while in both cases you have n going to infinity, then, yes, so I'll just write if n goes to infinity, then 2n plus 1 also goes to infinity. Yeah, and so in other words, you're going to have an an going towards an a infinity, and likewise, and I'll just put and a 2n plus 1, or 2n plus 1, not just n plus 1, 2n plus 1 is also approaching a infinity there. Yeah, so they're both going to infinity, so then they're both the exact same thing when you're dealing with infinities. Thus, I'll write limit as n approaches infinity of an is equal to L, and it is also equal to limit as n approaches infinity of a 2n plus 1. So hence it is true. Alright, so now let's take a look at question 4, and this one states, if the summation Cn times 6 to the power of n is convergent, then the summation Cn times negative 2 times minus 2 to the power of n is also convergent. Alright, so now let's take a look at the solution, and it's in fact true. And I have two solutions here, actually, two ways of solving this. The first one is solution 1. This involves the radius of convergence theorem for power series. So we can look at it here. So we can see this is the case by considering the radius of convergence theorem from my earlier video, and it's again for power series. These are both power series. Yeah, see how it's the same form. There's a coefficient Cn there, x minus a to the power of n. There's 6 to the power of n and negative 2 to the power of n. Those are both in this form. So let's take a look at this theorem. So for a given power series, just to recap on it, the summation from n equals 0 to infinity of Cn times x minus a to the power of n. So for a given power series, there are only 3 possibilities. So that's the key. There's only 3 things that can happen with power series in terms of convergence. So you have I, the series converges only for x equals a. In our case, a is 0, so it doesn't apply here. And the series converges for all x, or I, there is a positive number r such that the series converges if the absolute value of x minus a is less than r, and then it diverges if absolute value of x minus a is greater than r. And note as before, so this is only yeah, this part 3 or part I is only for the interval, or where this x minus a, yeah, it's less than r. But if x, when x equals to a plus or minus r, so at the actual endpoint, the series might converge or might diverge. That is, no information is known about the endpoint. So when x, absolute value of x minus a is equal to r, yeah, then there's you can't really tell. You have to do that other ways. You can't use this theorem there. So let's take a look at our case. So in our case, the series either converges according to II or III. So 3 i's there, or yeah, according to case 2 or case 3. So let's write this down. So we have absolute value of, actually not absolute value, I mean the summation from this one. We'll just write the Cn6x, and so it's assumed you're talking about from n equals 0 to infinity. So we have this absolute. We just use this symbology without the n equals up to infinity, but that is just assumed. So the summation Cn6n, so if we have this right here, this equals to, in power series form, this equals to the summation Cn x minus a to the power of n. And in our case, we have, write this a bit neater, we have x is equal to 6, and then the a is equal to 0. So in terms of convergence, we have three possible scenarios. We have I. So I is for x equals to a, but in our case, x is not equal to a because we have 6 is not equal to a, which is 0. So we don't have this. So this is, can't apply the first one. So now we either have the second case, so it converges for all x. So let's go like this. If it converges for all x, this is, I'll just write all x. And this one right here is, yeah, true. So this is, if this were the only case, this is true. Yeah, so by case 2, this would be convergent because this one right here, yeah, this is all x. So -2 is part of x. Or you're going to have, I'll just write or, I'll just put an or we have I, and this is where the absolute value of x minus a is less than r. And in our case, we have absolute value of 6 minus 0, like this. This just equals to 6. So in our case, 6 is less than r. So we have 2 possible scenarios. Yeah, so we have either, instead of putting a check mark, let's put this, either this or this. For, yeah, so basically when this 6, if it's less than the radius of convergence r. So we have 2 scenarios, this or this. And now we compare to the other series. So now we have this right here. This is the summation Cn, and then times it by -2 to the power of n. So compare this to the other series. So we have summation Cn. Now we have x minus a to the power of n as power series form. So we have this is equal to, yeah, Cn, or actually write the other way around. So we'll write this one here this way and this way. Yeah, so here just quickly pause the video and then switch things around. So we have this summation like that of Cn times -2 to the power of n. Now on this right side we have this summation Cn times x minus a to the power of n. So then in our case, what we have here is x is equals to -2, a is still equal to 0. Thus, it converges for 3 cases. So we have I. Let's write I like this. I is when x equals to a, but in our case, x is not equal to a. So it's not equal to a because we have -2 is not equal to 0, so we can't use this. Yeah, so we have the other case. So we have or this, or I. So we have all x. So it either converges for all x. Yeah, so if this was true in our case, if this converges for all x, then that would be also true. So the statement would be true, but it doesn't. Well, actually, it ends up being, well, all 3 could be, or these 2 could be true as well. So you could either have x minus a less than, x minus a in our case equals to -2 minus 0. Like that. So there's the x -2 minus 0. This equals to, well, this absolute value of -2. That just equals to 2. And 2 is less than 6, where 6 is less than r. So if we have this scenario, this is true. So this is less than 6. Thus, this is true. Well, yeah, so this one or this one would be both true. So So the statement is true. So this is true because if this converges, then you either have two cases where you have where x, so x is not equal to a, so we can't use that. But if for all x, if it's all x, it converges. Or you have this scenario where 6 is less than r and 2 is less than 6. So then that converges. So then this is true. All right, so that was solution 1, and that used that radius of convergence theorem right here. But now let's take a look at solution 2, so solve the same thing, but using the comparison test. So we can also see that the summation Cn times negative 2 to the power of n converges by the comparison test. So first recall the comparison test from our earlier video. So if we have suppose a series an, series bn like that with positive terms, so if you have if bn is convergent and an, all the terms an are less than or equal to bn for all n, then the series an is also convergent. Likewise, if the series bn is divergent and all the terms an are greater than or equal to bn for all n, then the series an is also divergent. So in our case, we can take the absolute value and show that the Cn, the summation of Cn times negative 2 to the power of n converges absolutely and hence converges. When it's absolute convergence, it's also equals to regular convergence. All right, so in our case, the comparison one, we're going to compare it with this bn there. So I'll just write this here. So the summation of this bn series, to make it the same notation as the comparison test, this equals 2, write this a bit neater, one more time. All right. Yeah, this equals to the summation, the one we're going to compare it with, that we know converges. This is Cn 6n. This is converges. So we're given that it converges. All right, so that converges, and now what we're going to look at is, let's take a look at the other term right here. An right here, and we're going to, instead of just using the regular one, because there's a negative there, we'll just use the absolute value of it. So Cn like this, negative 2n. All right, so now what this equals to was, well, it's going to be equals to, or actually better yet, just because we don't know what the Cn is, just to be more complete, just to remove that out, because it doesn't matter. It's the same thing as this one here, so it's not going to affect the comparison test. So let's just take the absolute value of that there. So then it's negative 2 to the power of n. So in other words, the negatives, anytime it's negative, it just becomes positive. So this is just equal to 2n, like that. Power of 2n. I just made it like that just because, yeah, the solution manual had this, well, it didn't even say that. It just said it converges absolutely. But I'm pretty sure it's better to write it this way, because Cn could be whatever. But it's the same as this one here. So hence this one converges, and now this absolute one, if you take the absolute value there, this equals to this, and yeah, the comparison test has series with positive terms. So yeah, this one, they just assume this is all positive, even the Cn. So might as well just include that as well. Let's just do that as well. Yeah, so we could actually just erase this and put that over both of these. And the reason is because these both have to be positive terms to use the comparison test, and the solutions manual said to use it. So I'm just going to assume they're both positive. So then, yeah, we're just going to assume that both of these are positive. Yeah, the Cn minus 2 to the power of n, and also this right here. So the Cn times 6 to the power of n. So assume that's all positive terms. So then we take the absolute value of this, then the Cn means it's positive. This one turns into positive negative 2 to the power of n. Just becomes positive 2 to the power of n. And now, yeah, what we have is now these terms right here, an. Yeah, this an is going to be, well, let's put this arrow like this. An is less than or equal to bn, since right here, since the only thing that matters is these ones, the Cn's are the same. So since 2n, we'll put this like that, since 2 to the power of n is less than or equal to 6 to the n. The only time it's equal is when you have n equals to 0, because number n is going to be greater than or equal to 0. If it's n equals 0, then they're both equals to 1. So since this is always less than it, then that means this an is going to be convergent, and in our case, absolute values are going to be convergent. Thus, the summation of the absolute value of Cn n minus and then Cn times negative 2 to the power of n, all absolute values, is going to be this converges. this converges like that. And yeah, so that converges, and so does, so that converges absolutely. Well, this regular one with this is without that absolute value here. So then this means then they both converge. So if it's absolutely converges, then the non-absolute convergence is also applicable too, and that is true like that. Yeah, right. This also converges. All right, and that's a check mark. So that is true. And yeah, we could read this over here. So since it converges absolutely, it therefore converges as per the earlier theorem from question 6. That was basically if it absolutely converges, then it converges. Very interesting. So now let's take a look at question 5, and this one states, if the series summation of Cn times 6n is convergent, then the summation, I think there's an extra space there, then the summation or the series Cn times negative 6 to the power of n is convergent. All right, so let's take a look at the solution, and this is in fact false, and let's go over this. So note that the radius of convergence theorem doesn't help us, so we can't look at this and get some useful info from it, and we can take a look at that. So let's do that same stuff that we did before. So let's say we had the summation of Cn, and then this is going to be 6n. Oh, so now it's 6n. We already went over that one, so let's put the negative 6 to the power of n like that, and write this in the power series form. This is going to be Cn and then x minus a power of n. So in this case we have, let's put this like this. X is equal to negative 6 in our case, and then a is equal to 0. Alright, so we have the 3 cases now. So we have converges for either, so I'll just put that for completeness, this sentence there. So for either, if we have I, so if we have x equals to a, in our case, x is not equal to a, and that's because we have x is equal to negative 6. So we have negative 6 is not equal to 0, where that is a over there. So then the other scenario could be, alright, so the second case, this is for, well, all x. I'll just put all x. So it's either all x. Yeah, so if this is the case, then it would be convergent, but we don't know that. And then we have the other case. It could also be this one here, where we have absolute value of x minus a is this equals 2. The number has to be less than r, the radius of convergence. And in our case, this equals to negative 6 minus 0. This just equals to absolute value of negative 6, which equals 6 less than r. Like that. And now this scenario right here is the same as for the other case, for the 6n, 6 to the power of n, if I scroll up here. So this is the same thing. We have, so it's either for all x or for 6 is less than r, so it's in one of these scenarios. So it's basically saying, that I either converges for all x, or for this scenario where 6, this right here is less than r, but we don't know that. Yeah, we don't know what this value of r is. This one could be, for example, if it was 7. So if it was 7, then this would be convergent. But it could be 6. So let's say if r is 6, then that's going to be at the endpoint, and we don't know if this will be convergent. Whereas this one, we're given that it's convergent here. Yeah, so we're given that this is convergent. So it could be that just at the endpoint of this x equals 6 is convergent. But then now we're looking at x equals negative 6, so we can't tell that. Yeah, so we could go scroll this here. So we could write same as for the other series, the Cn and then 6 to the 6, Cn to the 6 to the n. Yeah, but r could be 6, but r, right here. So, but if r equals to 6, then, or here I just quickly erased that and wrote instead, just because we could write more just quickly and so on. So this doesn't help us because if r of the radius of convergence equals to 6, then the series could converge at x equals 6, but not at x equals to -6. So in other words, the radius of convergence doesn't help us at the endpoints. Alright, so instead we can modify both series as follows. And to do this, we could just pick a value for the constant. So I'll write this here, let c sub n equals 2, so the coefficients there, -1 to the power of n over n to the 6n, like that. So if we have let this, then what we'll have is, then if we have the summation, the one that we're given, that's converges, so cn times 6 to the power of n, this equals 2, and now we're going to replace that in there, then we can just check if it actually does converge. This is going to be -1 to the power of n over n 6 to the power of n, then times it by 6 to the n, like that. So what happens is, well, this cancels, all we're left with is summation, then -1 power of n over n. And here we can check the convergence here. So we can apply the alternating series test. Here's from earlier video. Again, just recap on that, the alternating series test. So if the alternating series, summation from n equals 1 to infinity of -1 to the power of n minus 1, bn equals to b1 minus b2 plus b3 minus b4, etc. So alternates, and bn is always positive, greater than 0. And if this satisfies, bn plus 1 is less than or equal to bn, so it's always decreasing for all n. And that the limit as n approaches infinity of bn equals to 0, then the series is convergent. Alright, so let's take a look at our case here. So we have this series. So summation, let's go here. Cn 6 to the power of n is equal to, and then this series over there, summation from -1 to n, divided by n, like that. Then if you just put this inside, this is gonna be, well, let's start off with n equals 1. So this is n equals to 1 up to infinity, and n equals to 1 up to infinity. Okay, just so it matches this part right here. Now if you plug in 1 inside here, this is going to be -1 power of 1, it's going to be -1. And then the next one's going to be, when you put in a 2, it's going to be positive 1 over, and then this one's going to be 2, like that. So initially it's going to be 1 over 1, then 1 over 2, then this is going to be 1 minus, and then this is going to be minus the next one because it's be cubed, 1 over 3, and then plus, instead of 1 over 4, and so on. Then it's going to be minus plus. So minus plus dot dot dot. Again, so it's alternating and so on. So this is our B1 is just it just equals to 1 there. There's our B2 and so on. And B2 is less than B1 because that's 1 half. 1 divided by 2 is less than 1. Then 1 divided by 3, you're dividing by a bigger number. That's going to be less than the other one there. So then this is our B3 less than B2, etc. So these are all, they all continue on like that. So thus what we have is so the series, the alternating series test, thus we have I is this part right here, Bn plus 1 is less than or equal to Bn. So each one of these is getting smaller and smaller, the Bn's there. And that's the alternating setup there. So the Bn there, ignore the signs there. And then the next one is limit as n approaches infinity of Bn, or B subscript n. This equals to the limit as n approaches infinity of, this is going to be just 1 over n. And then 1 over n, this is just goes to 1 over infinity, approaches 0. So this equals to 0, like that. So then this is convergent. So I'll just say this is convergent by the alternating series test. Or actually just write instead over thus the summation of Cn 6 to the n, this equals 2 this is going to be negative 1 to the power of n over n. This converges. So this part right here, this is convergent by the alternating series test. And let's just box this in. So that is convergent, just to confirm. This is just the solution manual. They do something like this. So you have this one here, and then that converges. But now this is basically looking at an example of the scenario to show that whether it's true or false, or in this case, looking at if it's false. And yeah, we could do the same for the other series we have. And note that, remember, this is going to be false. So we're going to look at all we need is one example where this is not going to be true. So we have Cn like that. So if we do the same for the other series, we have, let's just write that down. So the summation Cn, now we have a negative 6 to the power of n. This equals 2. And then we're going to replace that with over here. So this Cn equals to negative 1 power of n divided by n times 6n at the bottom. So we have negative 1 power of n over n 6n, and then times it by negative 6 to the power of n. Alright, so what this ends up being is, so now we just simplify this. This is equals to, and let's just write this down, the summation. Now we have negative 1 power of n, and now this one right here, we can simplify this by putting this as a negative 1 power of n, so negative 1n, and now 6 to the n. So just put the n inside the brackets like that. Now this can be divided by n times 6n. So now this cancels, and now these combine. Oh yes, you can combine or add the powers. So then this is going to equal to the summation. And now it's going to be negative 1, 2n. So n plus n is 2n over n. Now this right here, this part right here, this is always equals to 1 because you have a even number there, so 2n. So if you have negative 1 to the power of 3 times 2, that equals negative 1 to the power of 6, and that is equals to 1. So it's always going to be, it's always going to be positive. And or you could even write this down as equaling 2. Right here is going to be negative 1. So we can put this squared inside. So negative 1 squared, and then this is going to be like that, all to the power of n. So same thing. This one's always going to be positive. Equals 1, so this equals to 1n equals to 1. So this means is we're just going to get equals to the harmonic series. 1 over n. Harmonic or p series, this is a divergent series. And this right here is, let's put this in square, this is a p series with p equals 1, which is divergent. And this is divergent. So hence we found an example where it is not the case. So it's so that if this is a convergent, this one is divergent, hence the claim is false. So box that out. Alright, so now let's continue further. Now look at question 6. And now this is looking at the same series of questions there, that Cn 6 to the power of n. So question 6, if the summation or the series Cn times x to the power of n diverges when x equals 6, then it diverges when x equals to 10. So now we're looking at divergence as opposed to convergence. Alright, so let's take a look at the solution. This is in fact true, and as per the radius of convergence theorem, the series diverges as per case 3, and you can see that above here. So the only time it's dealing with divergence is it diverges if the absolute value of x minus a is greater than r. Alright, so if we're given that this is divergent, just go back here. So if the Cn xn diverges when x equals 6, and it diverges when x equals to 10. Well, let's take a look at that. So let's look at that scenario again. So like before, so if we have, let's just write that better like this. Let's erase this. Alright, let's write that one more time. this is going to be Cn6 n, or actually I write that again, so Cn6n, or actually we're dealing with just a generic x there instead, so let's put this x like that, x to the n, and then in the other format like this, I'll just ignore that infinity, let's write this one more. Okay, so then this is going to be Cn and then x minus a, just write it in that other form. So we have a is equal to 0 in our case. So if x equals to 6 and it diverges, that means it diverges for, or I'll just write this here, or actually it's already given there, so it diverges when x equals to 6. This means that we have case or the case 3, x minus a is equal to, well, 6 minus 0, because x is 6, and this is going to be equals to 6, and this is greater than r. All right, yeah, so this is the scenario where the series summation Cn x to the power of n diverges when x equals to 6. So this means that thus put a bracket or comma, if x equals to 10, we have case absolute value of x minus a is equal to, well, in this case we're going to have, well, 10 minus 0, this equals to 10. This is greater than 6. Yeah, 10, this is greater than 6, and 6 is greater than r. So then this all matches up. So this is all true. So then it is divergent. So yes, diverges. Diverges when x equals to 10. Like that. Alright, here I just moved it over here. So diverges when x equals to 10. And now let's look at question 7. So question 7 states the ratio test can be used to determine whether the summation of 1 divided by n cubed, or the series, converges. Alright, so let's take a look at the solution, and this is in fact false. We can't use the ratio test. And to illustrate this well, first recall the ratio test from my earlier video on the, this is the video on absolute convergence and the ratio/root test. So the ratio test, if the limit as n approaches infinity of the absolute value of an plus 1 divided by an equals to L less than 1, then this absolutely converges and therefore convergent, and so on. But if it's equals to L and is greater than 1, or it goes to infinity, the limit, then it's divergent. But if it's equal to 1, then we can't use the ratio test. It's inconclusive. That is, no conclusion can be drawn about the convergence or divergence of the series an there. So let's take a look here. Let's just apply the ratio test and see what we get. So this is a summation from summation of 1 divided by n cubed. So we have, let's just write this like this. This is our an, the summation an, and in our case it's going to be 1 over n cubed. And then taking the ratio test, so limit as n approaches infinity of the absolute value of an plus 1, so the term after it, divided by an, equals 2, and in our case the limit as n approaches infinity of, and then now we're going to have a giant bracket here. So on the top, so we just plug in n plus 1 here cubed, so we're going to get a 1 divided by an n plus 1 cubed. Divide this by 1 divided by, well, just n cubed, like that, an all absolute value. And since n is always going to be positive, so either 0 is the lowest you can get, and this is cubed, so it doesn't matter what you do, these will always be positive, so this is always greater than or equal to 0. So basically we don't need to have the absolute value, so then we can just remove those. So this equals to the limit as n approaches infinity, so we can remove the absolute value signs. And also this is dividing by a fraction over there, so this one goes on top and this one goes on bottom. So this is the same thing as writing it as, so this one goes on top there, n cubed over n plus 1 cubed. And now we got to evaluate this limit, and well, the first thing that comes to mind is notice the highest power n to the cubed. So we could multiply the top and bottom if you recall our limit techniques over here. So we can multiply top and bottom by 1 divided by n cubed, so we can get rid of some of the n cubes there. And then this one here, this one n plus 1 cubed, yeah, that also will have an n cubed, so we're going to divide this also by 1 over n cubed. So then we're multiplying by this, so we're not actually changing this because these are both cancel out, so they're both 1, but we're going to do this just to manipulate this equation. Yeah, so the n cubes will cancel, so this cancels with this. And now this bottom part here, what do we end up with? Well, they have the same cube there. Yeah, 1 over n cubed. Basically, this is the same thing as writing, well, this equals to n plus 1 cubed times it by 1 over n cubed. It's the same thing as 1 divided by n cubed. And yeah, because this one here, if you 1 cubed is the same thing, then this one cubes both, so 1 cubed is still 1, and then n cubed, it will be this formula there. Now this one equals 2, we can combine the cubes, so we're going to have a setup like this, n plus 1 times it by 1 over n, and then put the cubed on top. Yeah, or put the cubed outside there. So now we have this, and we can multiply that inside. So what we'll get is, let's put the whole limit now. Limit as n approaches infinity. Now this n cubes cancel with that one there, so we have 1 over, and now this part here, we could just multiply that directly inside. So we're going to have a, this one will cancel with this. This and this will cancel, and this one will have a 1 over n there. So what we're going to get is a 1 plus 1 over n cubed, like that. Yeah, so that is what we'll have. There's put a cancel there. This one's going to be divided by n. This one goes to 1, that goes to divided by n. So anyway, so this is what we have. And as now that there's only one n variable, so in this one, as this goes to infinity, this part here, 1 over infinity approaches 0. So in other words, we're going to have, yeah, this limit is going to equal 1 divided by 1 plus 0 cubed. So in other words, that's just 1 cubed. This equals to 1. Like that. So that is our limit. So this equals to 1. So the ratio test is inconclusive. So like that. So I'll put here, so because it's 1, we go inconclusive. Inconclusive. So we can't use the ratio test for it. And I'll box this out. And here's fix up the box, put the arrows outside of the box. So that's inconclusive, so hence this is false. Alright, so now let's take a look at question 8. And this one states the ratio test can be used to determine whether the summation 1 divided by n factorial converges. This not capitalized. Yeah, so now instead of the other one, now we're going to check this one out. And let's just look at the solution. Delete this. So the solution is, well, this is true. So let's see what the ratio test gives us. Yeah, so again, the ratio test, but it's extra space. So the ratio test, we just have to do the limit of the absolute value of an plus 1 divided by an. So let's just write here. So in our case, this case, we're going to have an is equal to the series 1 divided by n factorial. So in our case, now we're going to have the limit as n approaches infinity of the absolute value of an plus 1 over an. This equals 2, and similarly to above, we're going to get limit as n approaches infinity. And then the top one will have 1 over n plus 1 factorial divided by 1 over n factorial. And once again, all this inside is greater than or equal to 0, so we're just going to have, always positive, so we could remove the absolute values. So this equals to the limit as n approaches infinity, and notice this part right here. So this one goes on top, and this will just be n factorial. Put this here, n factorial over n plus 1 factorial. And note that this n plus 1 factorial, this just means this is equal to, well, n plus 1 Yeah, this would just be n plus 1 times it by n factorial. Yeah, so that's just that, and then this equals to the limit as n approaches infinity of n factorial over n plus 1 times by n factorial. So these cancel, and we're just left with a limit as n approaches infinity of 1 over n plus 1. And here, just move things around just to fit it in. And yeah, so this is a limit as n approaches infinity of 1 divided by n plus 1. So this just means, well, this whole thing is going to be, well, yeah, this will just be, well, 1 over, n goes to infinity, so infinity plus 1, it's still infinity, so this goes to 1 over infinity and goes to 0. So in other words, this equals to 0. All right, here I just move this this little note on the top so that we could write this here. So this equals to 0, which is less than 1. We could box this out. And yeah, since this is less than 1, so that we go back to the ratio test. So this equals to L and it's less than 1, therefore it's convergent. So absolutely and therefore regularly convergent. So this is convergent. So I'll just write converges. Put the arrow, put a block around, and yeah, so that is convergent. All right, so let's take a look at question 9, and this one states if the an, this terms right here, an, the sequence, is less than or equal to bn and greater than or equal to 0, and this series of bn diverges, then the series an diverges. All right, so let's take a look at the solution, and this one here is false. So solution is false because this is just a comparison test. This is saying that if this is divergent, yeah, if this is divergent, this series bn, and the terms an are less than bn, then an doesn't necessarily diverge because if it's because all these terms are less than a divergent one. It's so it's the opposite of the comparison test. So the terms being tested for the comparison test must be larger than those of a divergent series or smaller than those of a convergent series. So if you replace these terms with convergent, then it would be true, because if bn is convergent, then all the values of an, the terms are less than bn, then that's going to be obviously convergent. But if it is divergent, these need to be greater than it. So yes. So otherwise, no useful information is obtained from this. Yeah, from this section right here. If all these terms are less than this, where bn diverges. All right, now let's take a look at question 10, and this says this is the summation from n equals 0 to infinity of this alternating series of negative 1 to the power of n divided by n factorial, and this is asking if this is equals to 1 over e. So let's check the answer. And here's the answer, or the solution. So this is in fact true. First, you can recall from the earlier table above. And here is that series for e to the power of x. So this equals to summation from n equals 0 to infinity of xn divided by n factorial. And this equals to 1 plus x divided by 1 factorial, etc. plus x squared divided by 2 factorial, x cubed divided by 3 factorial, etc. Thus, in our case, what we have is, so let's just write this down. So we have e to the x. We know that this is equal to the summation up to infinity from n equals 0, xn, divide this by, just nicely, xn divided by n factorial. Yeah, then in our case, we're looking at this e to the power of x. Yes, e to the x. So yeah, our case is 1 over e. So in our case, we have 1 over e equals to, well, this is the same thing as writing e to the negative 1. All right, so this means then we just replace x with negative 1. So this equals to the summation from n equals 0 to infinity of negative 1. So replaces x with negative 1, power of n, all over n factorial. Like that. And this is in fact the same thing over here that we're asked to see if it equals to it. So this is true. So let's put this like this. I'll box the whole thing out. True. All right, so now we could look at question 11. So this is true. So let's look at question 11. This states if you have this alpha is between negative 1 and 1, then the limit as n approaches infinity of alpha to the power of n is equal to 0. And let's look at the solution now, and this is in fact true. So recall from my earlier video on this. So this is from the squeeze theorem, infinite sequences, limits, squeeze theorem, Fibonacci sequence, etc., and golden ratio video/article. So here is from that video. So the sequence, the sequence r to the power of n is convergent if -1 is where r is between -1 and less than or equal to 1, and divergent for all other values of r. So now here we're dealing with sequences, not a series. Yeah, so here a limit right here as n approaches infinity of r to the power of n, you could write it as this, so equals to 0 if r is between -1 and 1, and equals to 1 if r equals 0. So it's both convergent, but if it's between these, it's equal to 0, and it is equals to 1 if it's r is 1. And yeah, so this would be true, and you could see this visually as over here. So the sequence an equals to r to the power of n, it can be seen visually for different values of r here. Yeah, so you have it here. So if r is greater than 1, basically you're going to have this alpha. So you're going to have, I'll put this r to the power of n. In other words, you're going to have, let's say for example, greater than 1. So you have 10 to the power of n. So this one's just going to keep getting bigger and bigger. All right, yeah, so this just gets bigger and bigger. And yeah, so you can see that here. Over r is greater than 1, the an just gets bigger and bigger. And if r is equal to 1, you're just going to have the sequence just keep going straight like that. So if 1 to the power of n, that just equals to 1 always. So you can see it just keeps going straight. And that is over here. And if r is less than, if r is between 0 and 1, for example, 1 over, for example, 0.1 power of n, that equals to 1 over 10. 1 over 10 to the power of n, like that. So as it gets, as you increase n, you're dividing by a bigger and bigger number, so it's getting smaller and smaller, like that. It goes to 0. And now if you look at the negative sides over here, so if r is between -1 and 0, so for example, let's say 0.1, so let's say -0.1, this equals to -1 over 10, like that, power of n, and this is going to be alternating, but it's going to be decreasing every single time. We're dividing by a big number, but it's going to be decreasing, and it's going to be flipping sides, it's going to go over to 0, like that. And in the other case, if you have r is less than 1, it's going to be alternating, but it's still going to be going to infinity. It's similar to this one here. For example, let's say you had r is equal to -10. So -10 to the power of n. This equals to, well, this -10 to the power of 10. And this is equals to -1 times 10n. So it's just going to be alternating bigger and bigger. Be bigger and bigger, alternating bigger and bigger. So hence, this is true. So if alpha is between these, and then in other cases, r, just replace r with alpha. So if alpha is between -1 and 1, then the limit as n approaches infinity of alpha to the power of n equals to 0. All right, so now let's look at question 12. And this one states, if the summation of the series an is divergent, then this absolute value of an is divergent. All right, so let's take a look at the solution, and this is in fact true. And this is true because if it wasn't, then the absolute value of the series right here, summation of an, would be convergent. Yeah, so notice here. So if this series is divergent, so let's say if this was true, if this was divergent, then over here, yeah, then this would be convergent if it wasn't true. So for example, but then this is absolutely convergent. And then this would make this convergent, so that wouldn't make any sense. So this is true because if it wasn't, then absolute value of an would be convergent, or I'll say would be absolutely, would be absolutely convergent. Hence then it's going to be convergent. Hence, I'll just put would be absolutely convergent, or I'll just put that in brackets like this. Hence, hence this also converges. So it doesn't make any sense. also converges. Hence, we have a contradiction. Because if it wasn't true, so if this is divergent, then this isn't divergent, this becomes convergent, but then this is absolutely convergent, so then the regular one's going to be convergent, so that doesn't make any sense. So recall from my earlier video, so if a series AN is absolutely convergent, then it is convergent. So you can't have this convergent and this divergent. In other words, if this is divergent, this also has to be divergent. So, but we are given that right here, the summation from AN is divergent, thus the absolute value has to be divergent too. Very interesting. Now let's take a look at question 13. Move this lower, like that. Alright, so if the series f(x) equals 2x minus x squared plus 1 divided by 3 times x cubed, then the next one's going to be minus, and then the next one's plus, etc., converges for all x, then the third derivative at 0 equals to 2. Alright, so let's take a look at the solution, and this is in fact true. And there's two ways of solving this. Let's look at solution 1. This involves the coefficients of a power series. So this is a power series, coefficients of it. Recall the formula for the coefficients of a power series. So this is if f has a power series representation or expansion at a, that is if f(x) equals to summation from n equals 0 to infinity of Cn times x minus a to the power of n. And the absolute value of x minus a is less than r, that's the radius of convergence. Then its coefficients are given by the formula Cn. So these coefficients equals to the nth derivative of f at a divided by n factorial. Thus, in our case, we only need to consider the third coefficient because we want to get where this is n equals to 3. Yeah, so this is going n equals 0, so the n equals 3 coefficient. I'll just put this like this. N equals 3. Coefficient, just because there's a 0 there, so that would technically be the fourth. So we just need to look at the n equals 3 coefficient there. So, yes, so let's just write this one out as this. So what we have is here. So we know that the coefficient Cn equals to f, the nth derivative at a divided by n factorial, and where f of x is equal to the summation, so as a power series form here, this equals to the summation up to infinity of n equals to 0, and then we have Cn x minus a to the power of n, and now this equals to, well, this a is equal to 0 in our case. So a equals 0 in our case, because you can see this x, there's no 0, there's no a there. So it's just x to the n. So then this is going to be 0. So in our case, it's going to be, well, we have 2 to the x, like that. And in this case, you can see there's a 0 there. For n equals 0, it just vanishes. So this would be power of 1. So this right here is our C1 equals to 2. And then the next term is negative x squared. Negative x squared. So this is going to be, well, C2 equals negative 1. And the next one's going to be plus. Now we have a 1 over 3 x cubed. X cubed, and then it goes minus plus dot dot dot. So we only need to worry about this one. That's going to be our C3 equals to 1 over 3. Alright, so what this means is, well, we could just take this this coefficient right there is 1 over 3 and throw that into this formula for n equals 3, and we can get the third derivative, or f triple prime, and then rearrange it to solve for what it is. So what we have is, well, C3, this equals to, well, f of the third derivative, just write it like this for completeness, a is 0, and then this is going to be 3 factorial. This equals to, it's the same thing as writing f triple prime, like that. Yeah, it's the same way as writing that derivative there, divided by 3 factorial. Now this equals to, well, we're given it's equals to this. So 1 over 3. So what this means is we could move the 3 factorial over to the other side. So what we get is f triple prime at 0 equals to 1 over 3. So 3 factorial divided by 3. And 3 factorial is equals to 3 times 2 times 1 over 3. This cancels, this cancels. 2 times 1 is just 2. So this is true, and yes, we're given converges for all x, then f triple prime 0 equals to 2, and that is true. So that's solution 1. That's just using coefficients of a power series. We know it's a third one. And the other solution is we could just do it all directly. Yeah, so let's take a look at that. So solution 2, so we could just differentiate f. Yeah, so we could just differentiate it or take the derivative of f multiple times. So we can also just take the derivative 3 times and plug in x equals to 0. So let's look at our f of x. So that's f of x, and let's take the derivative 3 times. So we'll start with f of x equals 2. So f of x equals 2, let's see that again, 2x minus x squared, and then plus 1 over 3x cubed. So this is going to be 2x minus x squared, was that over 2, I think? Let's go over here. Yeah, no, there's no over 2. 2x minus x squared. And then the next one is over 3. Plus 1 over 3x cubed. Yeah, so we have 2x minus x squared plus 1 over 3x cubed, and then it goes minus plus, etc. Minus plus dot dot dot. Alright, so that is f of x, and let's take the first derivative. So f prime of x is equal to, well, derivative of each term. So 2x derivative is just 2. And then this one here, if you recall the power rule, just goes down. So this 2x goes down and you subtract a power. The next one here is plus, the 3 goes down, 3 over 3, and then x squared, and it goes minus plus dot dot dot. Alright, and then these ones cancel, that just becomes 1. So then take the derivative again. This equals 2, well the derivative of 2 is just 0. And then this next one is the negative 2. And then here's going to be plus, well 3 over 3 is just 1, so then bring this derivative of this x squared, the 2 goes down. We have an x like that. It goes minus plus dot dot dot. Alright, and then the third derivative, f triple prime of x, is equal to, so this is 0, this one vanishes. Now here is a negative 2, goes to 0 as well. Plus, well, now we have a 2, derivative of 2x is just 2. And then it goes minus plus dot dot dot. And all these over here, let's put this here. Then this goes, all these terms here, all contain x. So that means, and then they go to 0. It goes to 0 as x equals to 0. So they all equal 0. Or better yet, when we plug in 0 there. So let's put that at there, not as. And then this one equals 0 at x equals 0. So plug that inside. So we get f triple prime at x equals 0 equals to, well, just 2. And everything else vanishes. And this is the same as what we were asked. So f triple prime of 0 is equal to 2. So the third derivative at 0. Alright, now let's take a look at the next question. That's question 14. And this is stating if the sequence an and bn are divergent, then the addition of the sequence an plus bn is divergent, and this one is in fact false. And yeah, let's go over the solution. So this is in fact false. So we can consider a simple case where two divergent sequences cancel each other out, thus giving a convergent sequence. So let an equals to n, and bn equals to negative n. Both of these are divergent, so as n goes to infinity, this goes to positive infinity, this goes to negative infinity. But an plus bn is, well, it goes to 0. This just equals to n minus n equals 0. So then so every single term is always going to be vanishing. So, n plus, with a plus, a negative, like that, equals to, well, n minus n. Just for completeness, equals to 0. And thus, the combination of the sequence an plus bn is convergent because all the terms go to 0. So then this is false. So if this is divergent, they're both divergent in this case, but then the addition is convergent. So this is not necessarily true. So hence it's false. So let's go look at question 15 now. Question 15 states if the sequence an and bn are divergent, then an-bn multiplication is divergent. Alright, so let's take a look at the solution. This is in fact false, and we can consider another simple case. Alright, so let's consider an and bn are the same, so equals to negative n like that, and negative 1 to the power of n. So this means these are both divergent because it's just alternating from negative 1 to positive 1, so plus, negative, etc. So it never converges, always goes, it always goes above and below, etc. So it never actually converges. And instead of putting this in line, it should be zigzag like that because you're incrementing by n like that. I'll put this further out here, etc. So this goes like that. Yeah, so, and it never converges for either of these. So they're both divergent. But then if you multiply them together, you have an times bn. This just equals to, well, negative 1 to the power of n times by negative 1 to the power of n. You can just add the powers, and then you have an even power. So that means it's always going to be positive. So this is negative 1 to the power of negative 1 to the power of 2n. You can just put the 2 inside the bracket. So negative 1 squared is just 1, and just 1n equals 1. Thus, an times bn is convergent. Hence, this statement is false. Does not have to be divergent. It could be convergent as well. All right, so now let's take a look at question 16. This one states, if the sequence an is decreasing, so it's always getting smaller, and an is greater than 0, so it's greater than 0, so in other words, it's bounded below, then an is convergent, and in fact, this is actually true. This is a monotonic sequence theorem. It's bounded. And so this is true. So solution is true since the sequence an is decreasing, it is monotonic. It's only going one direction, either increasing or decreasing, in this case decreasing. And it's bounded between 0, so it's greater than 0, and it's less than the first term a1 because it's always decreasing, then it is convergent as per the monotonic sequence theorem. Here's an earlier video. Recall this theorem. So every bounded monotonic sequence is convergent. So every bounded monotonic sequence is convergent. Now let's take a look at question 17. And this one states, if an is greater than 0 and the series, the summation of an converges, then you have over here the series, this alternating series, negative 1 power of n, the sum of this, or the summation of it, times an converges. All right, let's take a look at this solution here. This is, in fact, true, and you can just see this here. This is a alternating series, but if you just take the absolute value of it, it just becomes an, and you know an converges, so this means this would be absolutely convergent, hence that this is convergent. So basically this is stating that if this is convergent, this is this is also going to be convergent because, well, this is absolutely convergent, so that is actually the case. So note that the series, the summation of negative 1 to the power of n, an is absolutely convergent, hence convergent, so this is true. So what we'll have is here, I mean, when this is absolutely convergent, then this without the absolute value is also convergent. So if you take the absolute value here, just summation absolute value, and then the absolute value, this just goes to 1 there. Then this becomes absolute value of negative 1 to the power of n, because an is greater than 0. And so then we will have this just equals to, well, the series right here, and we know it converges. Hence, this absolutely converges, hence this converges by the absolute convergence theorem. All right, so now let's take a look at question 18. So this one states, if an is greater than 0, and the limit as n approaches infinity of an plus 1 divided by an is less than 1, then the limit as n approaches infinity of an equals to 0. All right, let's take a look at the solution here. And this is in fact true. This is just a ratio test. If it's less than 1, then that means it's convergent because this is, well, greater than 0. Then if it's convergent, then this sequence has to go to 0. So by the ratio test, the series summation of an converges. Since an is greater than 0, we can apply the ratio test. And here I just change up the sentence because it's not convergent because an is greater than 0. Just that since an is greater than 0, we can apply the ratio test and find that the series an converges. So here's a ratio test. Recall that the ratio test, if the limit as n approaches infinity of the absolute value of an plus 1 and divided by an is equals to L less than 1, then the series here, the summation of n equals 1 to infinity of an is absolutely convergent and therefore convergent. So we know that this converges because this is less than 1, and know that thus limit as n approaches infinity of an equals to 0 as per my earlier theorem, or as per the earlier theorem in my earlier video. Yeah, this is from the infinite series article/video. So if the series, the summation from n equals 1 to infinity of an is convergent, then the limit as n approaches infinity of an equals to 0. So hence, this is true. So it goes to 0 there. All right, now let's take a look at question 19. This one states 0.999999, etc. equals to 1. So if we view numbers as infinite series, then yeah, this is actually in fact true, as we'll show it. All right, so let's look at the solution. So solution is it's true. So we can write this as a geometric series. So let's take a look at this. So this is 5, 9. So we get 0.99999. This equals 2. You could write this as, I'll write this as 0.9. All right, so you could do as 0.9 and then, or yeah, just leave it as that, or even for more completeness, or actually no, we could just ignore the other part. So let's say we have 0.9, so we look at this part, then plus, take the same number here, 0.9, and now we're going to multiply this by 0.1 to the power of, well, 1. We'll just leave it at 0.1. So 0.1 times 0.9, this is the same as dividing by 10. So then this will get to this part here. This one right here is equal to 0.09. So we could, just for completeness, this equals to 0.9 divided by 10, which equals to 0.09. All right, so then that's this term. Then we could add the next one, 0.9 times it by 0.1 squared. All right, and now this part right here, this equals to, again, 0.9 divided by 100. Because this is going to be divided by 10 squared, that's going to be 100. Yeah, so each time you do that, it gets already at 10 squared. This equals to 0.9 divided by 100, and this equals to 0.009. Like that. That's this part right there. And yeah, we can see that it goes further and further. If you do the next one, it's going to be 0.9 times it by 0.1 cubed. And this is going to be, again, divided by 1,000. So that will be this part right there. All right. And so on. It's the next one to be plus dot dot dot. Here, I just moved everything over to the center there. Anyway, so now what this, we could write this as a formula. So this equals to the summation from n equals to, let's start at n equals to 1. Just make it the same as the geometric series format. So this is from n equals 1. So we have this as the initial right there, 0.9. Every single one has a 0.9. Times it by 0.1 to power of n. Initially 0, 1, 2. So we just put n minus 1. So when this is 1, this goes to 0. When this is 2, the second term, this goes 2 minus 1 is 1. And when it's 3, you subtract 1, so like that. It goes from 0 like that. All right, so we have this. All right, so now that we have this as a geometric series, we can sum this up. Let's put can. We can sum this up using the formula for the sum of a geometric series. And if we recall the geometric series, see where we can scroll over it. I'll just search geometric like that. All right, so there's a geometric series over here, and hide this. Actually, no, this is not the geometric series. This is the link there, but it's actually over here. So here's the geometric series. Recall geometric series, summation of n equals 1 to infinity of ar n minus 1. Yeah, this equals to a plus ar squared, etc. So it's convergent if the absolute value of r is less than 1, and its sum is this right here, a, the first term, divided by 1 minus r. And in our case, we have, well, r is 0.1. And it's going to be less than 1. So in our case, we can use this formula to get the sum of the convergent series. So, but if r is greater than or equal to 1, the geometric series is divergent. All right, so first term divided by 1 minus common ratio. So let's go back to the bottom there. All right, so we're back here. So let's sum this up. So we have, in our case, a. This is a. This is r. All right, r is 0.1. So we have a equals to 0.9, r is equal to 0.1, and this is, and we have the scenario where the absolute value of r has to be less than 1. in our case, it's going to be equal to, well, just 0.1. And it's less than 1. Thus, this is convergent. Yeah, so that's right, converges like that. Make this better. Alright, so continue further. Now just sum this up. So put this all in just completeness form, just write it all together. So the summation of the geometric series right here from n equals to 1 of a r to the power of n minus 1, in our case is equals to 0.9, like that, and equals to 1, 0.9, times it by 0.1, let's remove this like that, 0.1 power of n minus 1, this equals to a over 1 minus r, in our case it's going to be equals to 0.9 divided by 1 minus 0.1. And this right here is just equal to, well, 1 minus 0.1, that's just 0.9. Alright, let's just move this over here. So this equals to 0.9 divided by 0.9, so they just cancel, this equals to 1. Alright, so the sum is 1, like that. Yeah, so there it is, that's true. So that's just the geometric series. According to, yeah, if you look at an infinite terms format, that equals to itself. Oh, well, that equals to 1. You can just round, basically just rounding up. Alright, so now let's continue further and now look at question 20. And this one asks, if the limit as n approaches infinity of an equals to 2, then the limit as n approaches infinity of an plus 3 minus an, let's put this neater. Yeah, minus an equals to 0. And this is in fact true actually, because if you look at, if this limit goes to 2, then it doesn't matter what this n plus 3 is, it's also going to infinity. So it's going to be true. This is going to be also 2, and then you subtract the limits equals to 0. Alright? Alright, so let's take a look at the solution. And solution, yes, it is true. So let's write this out. So since we know that limit as n approaches infinity of an, like that, an equals to 2, yeah, then what we have is, well, the limit as n approaches infinity of an plus 3 is also going to 2. So in other words, in this part we have an is going towards a infinity, and in this one we have an plus 3 is going towards, well, infinity plus 3. Infinity plus 3 is just infinity. It doesn't matter. Yeah, so it's still infinity. It's just insignificant. So this goes to infinity plus 3, it's, in other words, is going to a infinity. So these are the same stuff here, over here. So same thing. Same thing. Alright, so thus what we have is, let's move the center. Thus, we have limit as n approaches infinity of n plus 3 minus an is going to be, yeah, this right here, this just equals to, by our limit rules, the limit of both. You could write these together. Limit as n approaches infinity of an plus 3 minus, write this one more time neater, an plus 3, minus minus the limit as n approaches infinity of an. And these both equal to, well, 2. So 2 minus 2 equals to 0. Like that. And just move it over here and check mark. Alright, so now let's take a look at question 21. So if a finite number of terms are added to a convergent series, then the new series is still convergent, and this is in fact true, because it doesn't matter how many terms you're going, because remember, we're dealing with infinite terms. Infinitely, it's convergent if you go into infinity, so it doesn't matter if you have a finite number of more to infinity. Similar to this, you're adding infinity plus 3. So the same for series as well. Alright, let's take a look at the solution. So yes, it is in fact true. So a finite number of terms doesn't affect convergence or divergence of a series, only an infinite does. So now let's take a look at question 22. So if this series, the summation from n equals 1 to infinity of an equals to capital A, I'm assuming it means it's convergent. And so if you're given that, and you're given this right here, let's write this a bit better. Yeah, and you're given that the series Bn from n equals 0, summation up to infinity equals to capital B, then the series from n, or series or summation from n equals 1 to infinity of an times Bn equals to capital A times capital B. All right, let's take a look at the solution. And also note this is the last question of the quiz. So this is actually false. So this is not true. And let's use some basic geometric series to test this out. We could just test, because remember, all we need is an example to show that it's false. So let's go over an example, a simple one here, like this. So an equals to 0.1 to the power of n. And so let that let the an equals that, and let bn equals to, well, 0.2 to the power of n. Yeah, so these are just geometric series. So then we have this. We have the summation. So we have this summation as from n equals to 1 up to infinity of 0.1. You could also 0.1 power of n. And just for completeness, to make it look like the geometric series in the theorem, so you could write this as n equals to 1, and then remove this out. So 0.1 times by 0.1 n minus 1 is power 1. So when you add those up, it's the same thing. Yeah, for example, if you plug in n equals 1 inside here, it just goes 0.1 to the power of 1, that's 0.1. If you plug it in here, it goes 0.1. 0.1 power of 1, that's just 1. But that's just 0.1. And then times it by 0.1, and then n minus 1, so 1 minus 1 is 0. So anyway, just for completeness. So this equals 2. We know this is going to be a 0.1. This is a. So this is our a, and this is our r. So they're both the same. So this is going to be 0.1 over 1 minus 0.1. So this is going to be our a. That's going to be our r. So they're both 0.1. And this equals 2. 0.1 over 1 minus 0.1 is 0.9. So you can multiply by 10 on both sides, and you'll notice that this will cancel out. Yeah, or you could just do that in your head. It's going to be just 1 over 9. So 0.1 divided by 0.9 is just going to be 1 over 9, and this is our equals to our a. All right, so that is for this one, for a. And now let's look at the second one. So then, and summation from n equals 1 to infinity of bn, let's go put this here, 0.2 to the power of n. This equals to, well, we could do the same thing over there, and it's going to be the same thing. It's going to be now 0.2 over, that's going to be our a, and this is going to be 1 minus r, which is going to be the same thing. R, because again, it's the same thing. We could separate it out, and all we're doing is replacing a 1 with a 2. All right, and this equals to, well, 0.2, divide this by 1 minus 0.2 is just 0.8. 0.8, so this equals to 2 over 8. This, and then you can cancel this as 1, that's a 4. And this becomes 1 over 4. This is our B. Now let's just box this out. So that's our B. So B is 1 over 4. A is 1 over 9. So together it should be 1 over 9 times 1 over 4. That's 1 over 36. We'll get to that in a bit. So thus, yes, we have that. Thus, now let's do the actual multiplication of the series. Thus, summation from n equals 1 of infinity. Now, if you multiply these two terms together, you're going to get 0.1 power of n times by 0.2 to the power of n, so an times bn, just to get it like this. This equals to, well, we could simplify this right here. Yeah, let's go here. So let's do some algebra. So this is the same thing as writing equals to, well, 0.1, the same power. Yeah, we could take this n out, make it outside of them both, or instead I'll just put it all together here. Just make it all neat over here. So n equals 1. This equals 2. 0.1 times it by 0.2. power of n, like that. And this one right here is 0.1 times 0.2. That's just equals to, well, 0.2 divided by 10 equals 0.02. So again, it's going to be another geometric series. So this equals to, like a summation, and move this down here. Scroll down here. It's going to be summation. Try this a bit better. From n equals to infinity. This is from n equals 1 to infinity. From n equals 1 to infinity. And this is going to be 0.02 to the power of n. Yeah, the power of n, like that. And now we can do the same thing, the geometric series sum. So a divided by 1 minus r. And this one, a, is going to be, well, 0.2. So this equals to, let's move this all over. Oops, I'll move this over. And move it over to here. So this equals to a minus, it's going to be 0.02. This is our a. Divided by 1 minus r, which is 0.02, which is also a. And this is, yeah, it's also a, this is also r. So this is our r. This equals to 0.0, yeah, this just equals to 2 over, 0.02 over 1 minus 0.02, that's just 0.98. And here, if we just multiply by 100 on both sides, this equals to 2 over 98. And then divide by 2 on both sides equals to 49 times 2 is 98. So 1 over 49, like that. All right, so that is what this multiplication equals to, but now if we do a times b, this equals to, well, we know a is 1 over 9, b is 1 over 4. 1 over 9 times by 1 over 4, this equals to 1 over 36. Like that. And this is not equal to, so these ones are not equal to each other. These ones, like this, so this is not equal to this. Not equal to each other. So this is, hence it is false. So hence this does not always, it's not always the case. You can't just make this, so that's not a theorem, that's just a false statement. Because it doesn't have to be true, as this example shows. So it's very, very interesting stuff. So yeah, that is all for today. And yeah, I just wanted to go over this review and quiz section of the end of the Infinite Sequences and Series chapter of my calculus book, just to recap on it, especially because I haven't done a math video in a long time. And yeah, it's a good way to get back in the groove, and hopefully you enjoyed this. And like always, you can always download these exact notes in a link in the description below. It's going to be also on the Hive blockchain and article format, so everything in the description and so on. So yes, pretty epic stuff. Anyways, that is all for today. Let's scroll all the way back. We are, yeah, going all the way back. All right. Keep going. It's question 6, 5, 4, 3, 2, 1. And so on. And like always, I'll put the timestamps to all these questions inside and in the description of the video. Anyways, that's all for today. Thanks for watching, and stay tuned for another Math Easy solution.